I hope we will speak in English.
Yeah.
That's why I'm here to
I will explain everything. My survey of my own.
English. No, I have to speak in English because it's the only opportunity you have. If you don't do it, you lose this opportunity, and we have to. It's not good, and you have to write.
I have an article publishing an editor, but I write.
No, we have to write English and the rest. Something that
But I think he said that.
I don't know if you have seen, but there are some examples. No? Okay, welcome back, everyone. So we're going to start today and then also continue on Wednesday with basic concepts, okay, that are fundamental to really understanding the analysis techniques we're going to be studying moving forward. Now, for those of you who are not in the sampling program and also taking methods of survey sampling, this is going to be kind of a quick overview of the kind of stuff that people in that course are going to be learning about how to actually design samples. Just as a reminder, that's not what this class is about. So these next couple days are really just to give you the fundamental background that you need about complex sample designs to help you to understand the need for accounting for these designs when we sit down and do analysis. Okay, so that's really the focus here. Okay, so just to kind of summarize the course objectives, right? We talked about the syllabus, but these are really the 5 main objectives that we have and that we want you to leave this course with a good sense of completing. First of all, we want you to develop a comprehensive understanding of what's meant by design-based estimation. Again, this is the big difference from what you learn about in applied statistics courses, is how to do design-based estimation and how to make population inference when you're dealing with data from complex samples. Okay, so that's just understanding the terminology and kind of the inferential framework that we're working in here. Second, we want you to acquire the ability to apply the concepts and the theory that you're going to be learning about to a range of different analysis problems that you'll encounter in survey practice. So we want you to develop the skills where basically no matter what kinds of data set you run into, you'll have a fundamental understanding of how to approach analyses of those data and what to look for in the data set when you're trying to understand complex sampling features. Okay? Third, we want you to learn how to use software. Right? There's a lot of specialized software out there that allows you to do these kinds of analyses. We want you to become very familiar with those software tools. We also want you to have the mindset that software is a tool. It's not the end all be all, right? We should not be having the software guide what analysis approach we use. We should select the appropriate tool for the analysis we want to do. Okay? Your approach should never be dictated by software. It's the other way around. It's just a tool that allows you to implement these procedures. Fourth, we want you to gain an understanding of how to interpret the results of these kinds of analyses of complex sample survey data, including looking for robustness and assessing the sensitivity of your results. Okay, so a very common point where people get tripped up when doing these kinds of analyses, we never want to say things like 95% of the sample has this feature, or 50% of the respondents have this feature. In this course, we're going to be talking about techniques that allow you to make inference for a larger finite population based on a probability sample. So all of the statements that we make in our conclusions are talking about a larger population from which the sample was selected. Okay? That's a key kind of fundamental inference framework that we're changing here. We're talking about making inference about finite populations. We're no longer talking about features of respondents or the sample that we have in hand. We're projecting from the respondents in our sample up to a larger finite population with our inferences. So that's a key difference here. And I'll keep reiterating that as we go. And then finally, fifth, we want to practice presenting survey results and discussing survey findings via the preparation of reports and these short scientific papers. That's where the final project comes in, is how do you go about writing about these kinds of results when you're doing these kinds of analyses of complex samples. Okay, so by the end of July, we hope that we will have met all of these objectives, and you'll have this as kind of a working framework moving forward as you start to encounter other types of data sets where these techniques might be relevant. Okay, so our key focus today and on Wednesday is these first two steps of an overall approach to the analysis of complex sample survey data. And we talk about this in chapters 1 and 2 of applied survey data analysis, this kind of 6-step approach to doing a thorough analysis of survey data. Most people, unfortunately, jump right to 4. It's just kind of human nature. You sit down with a data set and you say, oh, I can't wait to look at this variable or look at this relationship or do this now, whatever the case may be. That's wrong-headed. Okay? Steps 1, 2, and 3 are so much more important than step 4. Okay? And that's why we're going to focus so much on starting with the definition of whatever your objectives are. That's the whole point of the prospectus. Okay, what are you really all about with this analysis? What's the point? What are your research questions? What's the population that you want to talk about? Okay, what data set are you using? So that's key to start with, is just really laying out your objectives. What's the point of this analysis that you're doing? And second, in this context, before you even get to the data set, before you even open the first data set, run the first analysis, you have to understand the sample design. Okay, that's the key difference, again, from what you've learned about in prior statistics courses. That's so fundamental to the kinds of analyses that we're talking about here, is spending time to understand the design of the sample that was actually selected, that gave rise to your data set. Okay? Was it a stratified sample? Was it a clustered sample? Was it an unequal probability sample? Okay, we're going to talk about all those features, but as an analyst of these kinds of data sets, it's on you to understand the design of that sample and what needs to be accounted for when you do the analysis. Okay? And usually that comes from a careful review of the documentation for a given data set. So when you download one of these public use data sets like we'll be talking about, you don't want to just grab the data. You don't want to just grab the code book. You want to grab the documentation for the data set as well. And before you open the first variable, look at that documentation. Read about the sample design, read about the features of it, read about the need to use weights, see if they've actually provided some example syntax to use to do the analyses correctly, okay, to run the analyses the way that fully reflects these design features. That's always the first step to think about with these data sets. Documentation first, before you do the first analysis, okay? We'll talk about the other 4 steps as the course goes on, but right, remember, analyzing the data isn't until step 4 of 6, right? We really got to spend time on these first few steps to make sure that we don't make critical mistakes when we're actually analyzing the data, right? So that's going to be steps 1 and 2 are going to be our focus today and on Wednesday. Now, the second edition of Applied Survey Data Analysis has a website. They have included that web link here. We'll take a break from the slides and go visit this just real quick. Sorry. Okay, on this website, there's a lot of information, kind of background information, but arguably as a bookmark, I think one of the most important things about this website is this left-hand panel. So you see every single chapter where examples are presented, we've replicated the code in SAS, Stata, SPSS, IVEware, which is a Michigan software product, Sudan, R, Westfair, and M+. Okay, so all the different examples that we'll be talking about, you can see the code to do this in basically whatever software you want to use. And my co-author, Pat Berglund, is working on updating all of these different examples as we speak, but the fundamental syntax that you would need for the replication is there. You also see links to data sets that we'll be talking about, links to websites for software, supplemental code that we've provided in addition to what's already in the book, and then a variety of different journal articles and publications talking about new and recent developments, okay, in this particular area. So take a look at this website. I think it's a good thing to bookmark, especially if you have colleagues who are using a variety of different software. But as we go through the different examples, you'll see the value here, I think, in looking at all the different types of syntax and executing the syntax here to replicate the analysis examples, okay? And certainly we have errata here as well. So if you see anything weird or something doesn't make sense in the second edition that's not already documented here in the second edition errata, please let us know, and we'll make sure to incorporate that hopefully in the next edition. Okay. Okay, so that's the website. I think, again, good thing to bookmark moving forward for the larger course. Okay, so conceptually, we want to start with this idea of what is a complex sample? Okay, what do we mean when we use that term, complex sample survey data? Okay, so it's good to start with some history. Those of you in the sampling program heard Jim's Jim loves to talk about history. I mean, that's why we started kind of late here. Is one of the co-directors of the sampling program, gave a good history of ISR and where everything came from. But when Jim talks about history, it goes a little bit longer than sometimes we hope. But this gives you some perspective about where the analysis side of things came from, okay, in terms of what gave rise to the techniques that we'll be talking about in this course. Really up until the 1930s, the only efforts that people made to try to make statements about populations were attempted censuses, where you literally tried to collect data on everybody in the population. Okay, it wasn't until the 1930s when people started to think seriously about sampling and how you could use sampling to make inference about what's going on in some larger population with reasonable accuracy and precision. So this 1934 paper by a Turkish statistician named Jerzy Neyman, okay, was arguably one of the more critical developments in terms of our entire area of the world here, in terms of making inference based on samples. Neyman presented a general theory of how to make inference about a finite population based on a probability sample, okay, primarily focusing on stratification, but really laying the groundwork for all the inferential procedures we're going to be talking about. That is the paper where the term confidence interval was introduced. Okay, so when you hear about a confidence interval, the idea first came from that paper where he basically said, I propose to call these limits confidence intervals. And that gave rise to the term moving forward. Okay, so starting with Neyman's theory, there was an explosion of work on how to make inference based on these kinds of probability samples. That was about the time of World War II. So there were a lot of public opinion surveys going on about the war, people's attitudes, people's opinions. And then starting with the post-war years, people started focus on how we can make data available for larger research purposes. That's about the time, like Jim said, when ISR came into development. Okay, the origins of ISR, where people were doing research based on surveys and also making these efforts to make data available for other researchers to work with. Okay, so up until that point, 1940s, 1950s, when people were working with survey data, the focus was primarily on descriptive analysis. Okay, so means, proportions, what proportion of the population thinks this or that, how many people think the economy is in good shape, what proportion of people are unemployed, things of that sort. But then in the 1950s and 1960s, people started to see, well, we can use survey data to study relationships between variables. And what's the appropriate way to go about that? That's what we refer to when we say analytic uses of survey data. Analytic really primarily referring to relationships between variables. Okay, that's when that started to become more popular. This gave rise to the need for software. More and more researchers were talking about making use of survey data. So in the 1960s, 1970s, that's when the first software began to be developed and the mainframe computer first became available for people to use. And that, once the software available, gave rise to more empirical computer simulations, trying to understand different approaches, different methods, a lot of work in that regard. And that led to more work on estimation techniques, inference techniques that were now possible with higher performance computing. And now we're living in a world where you can run these procedures, highly complex procedures, in milliseconds with the software that we have available in R and Stata and SAS. I mean, pretty much anybody can grab one of these procedures and run the right procedure on a given survey data set. It's whether or not that analysis is addressing your objectives, and it's whether or not you can interpret the results of those analyses correctly. Okay, that's what our primary focus is going to be. And even now, this is a very active area of research, theoretical development, better approaches to design-based analysis, all kinds of good stuff. Like I said, on the webpage, we have all these new articles talking about different developments in analyzing complex samples. And there's all kinds of new challenges that we'll be talking about as we touch on these different techniques where more work remains to be done. So as we go through the course, I'll continue to talk about areas where dissertations need to be written, about how to extend a certain method or how to fill in a gap in what tools are available for doing analyses. So we'll continue to talk about that and the research that's going on. But that's kind of a history. So it's, relatively speaking, not that old of a science, right? That we're this idea of making inference about larger populations. So when we talk about complex samples, the one thing to recognize is that every type of complex sample that we talk about is a probability sample. Okay, so those terms are going to go hand in hand in this particular course. When you hear the term complex sample, that implies that you're dealing with data from a probability sample. So what do we mean by data from a probability sample? In a probability sample, every population element has a known non-zero selection probability. Okay, we can write down that probability of selection for every element in the population. We control those probabilities of selection. Okay, they're under our full control as the person designing the sample. All right. So that is a key defining feature. We can compute the probability of a given element being included in the sample based on the design of that sample. It's entirely under our control as the person designing the sample. So given those probabilities, we can use those probabilities of selection to determine weights for each of the individual cases that were included in the sample. And when we properly weight our estimates, we can provide unbiased estimates of population parameters that we're interested in. Everything is governed by those known probabilities of selection, okay, for the cases in our sample. We know them, they're non-zero, we have them for every element in the population in the case of a probability sample. Furthermore, on top of computing unbiased point estimates, we can determine unbiased estimates of the variability of those point estimates. That's that additional piece that we need to worry about, is how can we describe the variability of those estimates? If we were to go out and draw thousands and thousands of samples using the same design, what would the variability of all those computed estimates look like? Based on one sample, we can compute an estimate of that variability of all the estimates. That's what we call a measurable sample design. A sample design that enables us to compute an estimate of that sampling variance based on one sample only. That's the wonderful thing. We don't have to go out and draw thousands and thousands of samples in this framework. We just draw one probability sample, and then we can use that probability sample to estimate the variance of the overall sampling distribution. We just need to do that correctly so that we're getting the right estimate of that sampling variance. Okay, so probability samples are measurable samples in that we can estimate this kind of variability. So the simplest kind of a probability sample is the one, again, that you hear about in Introduction to Statistics, the idea of a simple random sample. A simple random sample is itself a probability sample. And the features of that sample, every element in the population has an independent and equal chance of being selected for observation in the survey. So every population element in a simple random sample has the same probability of being selected. And those probabilities are all independent of each other. This is really the closest population sampling analog of what statistically we might refer to as IID data. or independent and identically distributed data. Okay, this is the type of sampling mechanism that will generate IID data. Okay, and all those procedures that you learn about in your first applied statistics courses generally assume that you're working with IID data. So in a population sampling analog, the assumption is that you're working with data from a simple random sample. Okay, none of these complex samples are simple random samples. That's the disconnect. And that's why this class is so important, right? We're going to learn about the techniques that you need to go above and beyond what you've learned about dealing with simple random samples and figure out how to account for these complex probability samples when you do the analysis. But it's not to say that a simple random sample is not a probability sample. It just got a very specific design where everybody has the same probability of being included. Okay? Makes it easy to apply a lot of techniques. We don't have to worry about weights. We don't have to worry about dependent observations based on the design of the sample. IID data in terms of how they're generated. Okay, but we're learning about complexities that need to be accounted for when we do our analysis. Okay, so simply put, a complex sample is anything in terms of a probability sample design that's more complex than SRS, more complex than a simple random sample. What are the features that make a complex sample complex relative to a simple random sample? Three main ideas really that give rise to a quote unquote complex sample. First, stratification, stratified sampling. The idea that you divided your population up into these mutually exclusive groups and you drew samples of design sizes from every single one of those groups or every single strata. Okay, all the strata. Okay. That is the first kind of complexity that adds complexity relative to simple random sampling. We allocate the sample separately to each of the different strata, and then we draw samples from each of the different strata. Okay, we're going to talk about why that's important. Second key feature of complex sample designs, cluster sampling. You're not randomly picking elements from a list of the population like you would in simple random sampling. Instead, you're sampling clusters of elements from some lists of many clusters. These could be schools, businesses, hospitals, neighborhoods, enumeration areas. They're clusters. Sometimes we don't have a list of all the elements in the population, but we do have a list of all the clusters. Okay, so instead, we draw a probability sample of those clusters. Then we go visit those clusters and we randomly select our elements, all the while maintaining those probabilities of selection. Okay, it's often a necessity just based on the materials that we have available. But people within the same cluster tend to be highly correlated in terms of what we're trying to measure. And we need to account for that when we're actually analyzing the data. So we need to recognize that feature of the complex design when we actually analyze the data. Okay. Third main feature, weighting. Okay. Under a probability sample design, not everybody is going to have the same probability of selection, like in a simple random sample. The person designing that sample might want to oversample certain groups, or areas with a higher population may have a higher probability of being selected. Those of you taking methods of survey sampling, you're going to learn about probability proportionate to size sampling. Okay? Clusters may be selected with different probabilities. That gives rise to different probabilities of selection that need to be accounted for. There may be adjustments to weights for non-response. People have different probabilities of responding to the survey. All of that gives rise to different probabilities of being included in the data set. We need to make sure those different probabilities are accounted for via the use of weighting. Okay, so any one of those three key features makes a sample design more complex than a simple random sample. Okay, anything more complex than a simple random sample is referred to as a complex sample. Now, why do we do any of these things? There are reasons: administrative reasons, statistical reasons. Cluster sampling saves money. We don't have to send interviewers out to randomly sampled addresses all over some large area. We instead send them to clusters, and they can work more efficiently. Okay? Why do we stratify? It reduces the standard errors of our estimates. Stratification always helps in terms of the precision of our estimates. Why do we weight? If we oversample certain subgroups, those weights are needed to map that sample back to the population. Make sure we're talking about an unbiased statement about a population not a sample with an excessive oversample of a particular subgroup. Again, we're not talking about X% of the sample says this. We're talking about X% of the population says this when we do our analyses, okay? So there's reasons for all those complex design features, but all it takes is one of those design features to make a sample complex relative to SRS, okay? With those weights, we can calculate unbiased estimates of our population parameters only with those weights, and we can calculate measurable sampling error. Okay, again, we can estimate variance based on these design features. Statistically, what we have to worry about is that IID case of simple random samples no longer holds. Okay, we need different procedures for non-IID data to be able to analyze these data, make representative statements about the population. Okay, and as we talked about, equal probabilities of selection may no longer hold as well. We need to account for that when we do our analysis. Okay, where are these kinds of complex probability sample designs used? They're really the rule and not the exception in a number of different fields that use sampling. The social sciences, epidemiology, public health, political science, agriculture, natural resources. Any of these fields that do any kind of work based on samples are going to tend to use complex probability samples. Simple random samples are very, very rare in actual research practice. For all the reasons I mentioned, complex probability samples are often used. Again, the rule, not the exception. Common types of designs that you'll run into when you read that documentation, area probability samples of household populations. So instead of just going out and looking at a simple random sample of households, you sample areas of households, and then you sample households within those areas, counties, enumeration areas, census blocks, okay, predefined areas where there are many different households. Multi-stage samples of schools, classes, and students in an educational setting. You might sample school districts, and then schools within those districts, and then classes within those schools, and then the students within those classes before you actually do the survey data collection. Okay, that's another example of a complex probability sample design. Okay, in an establishment survey setting, okay, you might sample businesses or hospitals, and then identify a reporting agent of that establishment who can respond to your survey. That's not asking about people who work there, but it's asking about features of the establishment itself. In those establishment surveys, they may be stratified into different types of establishment based on size or based on income or something like that. Okay, all that stratification needs to be accounted for when you do those kinds of analyses. Other types of designs you'll run into, dual frame samples, like sometimes you'll see a sample that has landline telephones and mobile phones. Okay, example of a dual frame study. Split plot sampling in agriculture, okay, where you divide a plot up into many different regions. You draw samples of soil or something like that from those different plots. RDD telephone samples. Those can be complex in nature as well. Certain areas are oversampled, or certain area codes tend to be oversampled. Natural resource samples. Okay, we draw more samples early in the morning than in the evening. Okay, something like that. Oversampling from particular times of day. Oversampling from particular locations. So you're seeing a flavor. It doesn't just have to be people. It could be businesses. Could be animals, could be natural resources, the same ideas hold. And probability sampling is used in these cases. Okay, so it's really a lot more common than you think, and that's why it's so crucial to understand the features of the sample design, depending on what context you're working in, what kind of data set you're dealing with. Okay, so I really, really like this picture. This was originally created by a company here in the United States called Westat. This is created by one of our colleagues at Westat to illustrate the idea of a complex multi-stage probability sample from a pretty large population, in this case, the entire United States. So this shows you the multiple stages that often define these kinds of complex probability samples, especially when, again, it's very difficult to collect data from a simple random sample. And we need multiple stages of cluster sampling to save on costs. So in a typical national survey of the United States, at the first stage of sampling, we call these primary sampling units or PSUs. We typically start with counties or groups of counties. There's about 3,100 counties in the overall United States. Some of them might be combined if they're smaller, but we typically start with those purple squares. which are counties in the United States, called those primary sampling units. So we might draw a probability sample of those counties to start with. And again, the objective here is a household survey. Within one of those sampled counties, we might then divide that county up into area segments. Okay, so counties can be big areas in the United States. Again, hard for an interviewer or a field researcher to work. So we look at all the possible areas within that county, and then we draw a probability sample of area segments within that county. Those are those yellow, uneven sized areas within that purple county. Okay, again, all for the point of saving costs. Even when we sample that county, we don't want a simple random sample of addresses within that county. It's a lot of driving, a lot of transportation, a lot of gas, right? We're trying to make the job easier for the data collectors. Okay, so we have then a probability sample of area segments. Within one of those area segments, then we might list the households. We might buy a commercial list of all the addresses within an area. We might send a person out to that area to canvass all the different housing units and write down their own list. Or maybe they update a commercial list. But we create a list of households within that sampled area segment. Then we draw a sample from that list of households in that area segment. Then we send somebody out to knock on the door. Okay, they might do a complete roster of everybody in that household. Okay, how many people live here? What are their ages? What are their races and ethnicities? So forth. Then we might ultimately be interested in sampling one person from that household to actually take the survey. Okay, and then those of you who've been working in data collection for a while, you go through all this stuff, all these stages, and that one person slams the door in your face. Right? That's the reality of survey data collection, non-response. So even after these 4 stages of sampling, there's an additional unknown probability of self-selection. Those are the people who don't respond to the survey. We have to account for that as well. Okay? So all of this gives rise to the ultimate data set of individuals that we want to work with. And all of these features of the design need to be accounted for in our analysis. That's what this class is all about. Okay? So again, those of you in methods of survey sampling, you're going to learn all about this stuff. But for the sake of just learning about how to approach these kinds of analyses, these are the key features that we need to account for when thinking about these probability samples. Okay?
Question on the diagram.
Yes.
Is it sampling stage 4 is sampling the sampling PSPs, is that sampling populations?
Oh, sample persons. Yeah, sorry, Sarah. Yeah, so the SP abbreviation here is for sample persons. SPs. Sorry, I should have clarified that. Those are the people who are basically eligible for sampling within each of the different households. And usually we'll take one of them. Sometimes the survey will ask for information from everybody in the household. Yep, those are the sampled persons. Yep.
It's like before RDD telephone.
Yes.
RDD.
RDD is random digit dialing. So that's where you're generating a sample of telephone numbers and then dialing those numbers at random. This is becoming more and more difficult in the US. There are policies and laws against just spamming people with random calls that survey researchers are trying to figure out how to work around that. But RDD stands for random digit dialing.
In terms of the SE, when we are seeing the probability of selecting are we talking about the person whose information you get at the end of the day?
Yeah.
So if you are randomly selecting one person in the household,
yep,
but you're calling, that person will respond and with all the other members of the household.
Possibly, yeah.
Or is it just I'm just trying to, because that thing comes out about especially.
Yeah. It depends on the objective of the survey, right? So are you trying to collect data on the entire household, or are you just asking about individual views, opinions, circumstances, and so forth? Sometimes you're trying to look for a knowledgeable reporter about, say, the finances of the household or something like that, where they'll actually be asked questions about things like how much does your household make, things like that. In that case, maybe only adults will be eligible for the survey data collection. But if the survey is only seeking to collect information about individuals, it may not matter. So it really depends on the objectives of the survey. And at that point with the SPs, the survey designer can say, at that step, we want to give higher probabilities of selection to, say, African Americans or Hispanics. So once you're in the household, if there are 5 eligible people, Not everybody has the same chance of being selected, right? So you may by design choose to oversample particular subgroups at that step. And that introduces unequal probabilities of selection. So who is sampled, who's eligible for sampling, and what they're asked about, it entirely depends on the objectives of the survey. And whether or not you're oversampling at that step, that needs to be reflected in your probabilities of selection. So we'll continue to see examples of that. Yep. Great questions. Other questions so far about these ideas here? Other questions online or? Okay, so we'll keep coming back to these ideas. To make it a little bit more concrete, I'm going to map that map onto a real survey that we're going to be working with in the class, the National Health and Nutrition Examination Survey. So the NHANES is one of the major national health surveys here in the United States. It really gets in detail about a lot of physical measurements, medical history, things of that sort. And it first started in the early 1970s. Okay, that was the first major NHANES, NHANES 1. And you can see there were different cycles of NHANES, NHANES 2, NHANES 3. Starting in 1999 up until the present, NHANES has really been done in a continuous manner, and they release data in 2-year cycles. So when you download an NHANES data set from online, you'll see basically a 2-year cycle that combines the data collection done in those 2 years. Applied Survey Data Analysis uses the 2011-2012 data set just as an example. But pretty much most of the NHANES data sets all have the exact same format. They're just coming from different points in time, right? So when we work with NHANES examples in ASDA and in class, we're going to be using that 2011-2012 cycle from that 2-year period. And that leads up to even now. Those are the 2-year cycles that get released. Okay? The SPs, or the sampled persons that Sarah was asking about in the NHANES, are interviewed about health and health-related matters. And what's unique about the NHANES is they undergo medical examinations in what are called mobile examination centers, or MECs. These are literally semi-trailers full of medical equipment, full of doctors, full of nurses, that the Center for Disease Control drives to a particular sampled area. And they post up in that particular area, and they invite sampled individuals from that area to come get their physical examinations, blood draws, all that kind of good stuff. Okay? So this is the very definition of why cluster sampling is so important. They could not drive that giant semi-trailer full of all this medical equipment to an individual's household somewhere in Wyoming. It just doesn't make any sense, right? From a cost efficiency perspective, they instead draw a small sample of areas in the US, and they drive these MECs to those areas. And then they invite people from those clusters to get the measurements collected. Okay? That's why cluster sampling is necessary in this case. So you can go online and you can see pictures of the MECs that the NHANES uses to invite people to get these physical measurements. Furthermore, the people funding the NHANES, they want separate estimates for different domains of people in the United States. So age, sex groups, African Americans, Mexican Americans, people of all other race, ethnicity, adolescents, elderly individuals, Mexican Americans and African Americans are oversampled by design. Okay, so areas with higher populations of these subgroups get a higher probability of being selected into the sample. That's part of the stratification, right? That information is used to divide the population up into areas with different densities of these individuals. And then areas with higher densities are oversampled. Even at the level of the household, individuals with these characteristics are assigned a higher probability of selection. The selection is still random. Somebody just has a higher probability depending on their characteristics, all to meet the objectives of the people funding the NHANES. They want larger samples from each of these groups. So if you're to put the data set back together, it's not going to look like the US. It's going to have an oversample of people from these different groups. That's why we need weights. If somebody was to sit down with the NHANES data set, ignore the weights entirely, and just go about their analysis, they're not going to get an unbiased picture of what the US looks like in terms of health because of the idea of oversampling these subgroups. The weights map that sample back to the target population. And that's the scary thing about what's going on out when people are doing secondary analyses. We were actually given a grant from the National Science Foundation here in the US to do a study of how often people analyzing these kinds of data sets actually account for the design features. What do you guys guess is the proportion of researchers who account for these features when they're sitting down to analyze these data sets, even today in 2024? What do you guys think?
It's very strong.
So we found in that study that only 50% of these articles use the weights. So arguably, 50% of these articles are presenting biased pictures of the population, peer-reviewed journal articles, okay? And only 1 in 10 are doing variance estimation correctly.
What portion of those 1 in 10, actually, I'm curious, are actually those who are like working with the working with samples, are employed by the organization that's actually conducting these? I think that would definitely skew your results.
Yeah, no, these are secondary analysts who, again, the kind of training that you guys are going to be receiving this summer is just not part of some kind of quantitative training program. So these are individuals who are perfectly well-meaning. They have a data set in front of them. They're analyzing that data set with the techniques they know and they've been trained in that don't include these issues. And then if you get 2 or 3 reviewers who are in a similar boat, they look at your analyses, they say, sounds great. Gets through peer review, gets published. People start fretting and worrying and saying, only 30% of the population is looking for a math and science degree. It's actually like 50, because those weights have been ignored. It's a problem. And that's why the training you guys are going to receive here is so important. We want to prevent those kinds of errors from happening. Okay? But these are the real features of a real study that give rise to the need for accounting for all these features when you actually do the analysis. We'll just keep driving that point home. Okay? So the multi-stage and Haynes design matches pretty closely with that picture we saw. At the first stage, the primary sampling units are mostly single counties. Those counties are stratified. They're divided into different areas by region of the United States and also by what's called metropolitan statistical area status. So is that county really a population density, a high density population area like Manhattan or Chicago or Los Angeles, where there's a lot of people, okay? They're stratified based on that criteria. And then those counties are selected with what's called probability proportionate to estimated size. Bigger counties, higher probability of selection. So right off the bat, unequal probability of selection. That needs to be accounted for via weighting. Right off the bat. We're still 3 stages away from actually selecting people. And we already have unequal probabilities of selection. There's nothing wrong with that. It's perfectly by design, but it introduces a feature of the sample design that we need to account for in the analysis. Okay. Second stage, same idea. Within those counties, area segments are sampled. These are typically blocks or combinations of neighborhood blocks with at least 200 to 250 people living there. Those are the sampled area segments. Again, they're selected with probability proportionate to estimated size. Bigger segments, higher probability of selection. And then the third, what's it? Yeah, so this is all clusters. So the PSUs are clusters, the area segments are clusters. All of those are clusters of elements that are sampled first before we actually sample the elements. Yep, George?
Let's find out at the first stage
Yep.
or the primary stage, how do you ensure that those quantities that are relatively small in size are sufficient? Because this is more proportional size, so those that are bigger, they tend to be selected.
Yeah, it's still random, right? So although the bigger counties might have a higher probability of selection, those smaller counties still have a probability. It's just lower. That's all. Because you want to try to hit the counties that have more of the population present. So those smaller counties still have a probability of being selected. It's just not as high as the bigger counties. And it's up to the people designing the sample how different those probabilities should be. Right? You guys, again, will learn about PPES and methods of survey sampling. But as the people designing the sample, you have full control over what you want those probabilities to be. Right? The key thing about secondary analysis is that the analyst needs to be aware that a probability sample was selected. They need to be aware of the weights and so forth. Right? Last one.
The first at the primary stage, you use weights.
Well, there are probabilities of selection that are introduced via that unequal probability of selection of counties. That gives rise to the need for weights right away. The weights aren't computed until all those probabilities have been accumulated across all of these stages.
Yeah.
Right?
Because the counties have different populations.
Exactly. Yep. So we have an initial weight if we're going to talk about multi-level analysis way down the road in the class, right? But if you want to do a multi-level analysis where you're estimating between county variance or something like that, you need those weights for the counties. You need the weights at each of these different stages. But for what we're learning about right now, those weights come from accumulating all these probabilities across these stages. So we wouldn't compute the first version of that weight until we know all those probabilities across all 4 of these stages. Yep. Okay, so third stage, again, we list all the housing units in that area segment, and then we sample housing units from that prepared list. Sometimes at this third stage, that's where you might have a simple random sample. You have a list of 30 housing units within a particular area. You draw a simple random sample of 10 of them, or whatever the objective of the study is. Okay, that might be a simple random sample, but you still have unequal probabilities at the earlier stages. Okay, they need to be documented and accounted for. Then you send somebody out to the household to learn about who's living in that sampled household. How many people are there? How many African Americans are there? How many Caucasians are there? Et cetera, et cetera. Okay. You classify people by the domain of the study that they're interested in, age domains, race, ethnicity, education, whatever the focus is. You try to understand the features of the people living there. Then, once you have that information, you take a probability sample of one individual from that household or maybe multiple. But once you have that information, then you can decide to oversample people if you want, if that's the objective of the design, an additional unequal probability of selection. Even if you're taking one person at random without any respect to any of these demographic features, a household with 5 eligible people, they're going to have a different probability of selection than a household with 2 eligible people, right? Because you're always taking one person from the household, different probabilities. So you could have an equal probability of selection approach all the way up to the household. Even then, there's going to be different probabilities of selection. Suppose you're doing RDD, right? And you ask a person, oh yeah, I have a cell phone and I have 3 landline phones. They have a higher probability of being called than a person who just has 1 cell phone. Unequal probability of selection. Okay, same idea. So the survey weights reflect whatever subsampling is done at that point of the household. So you go through all this work. Again, you pick a person, you call that person, you schedule an appointment, they never respond. Right? That's the reality of survey research. We try to maximize that response rate, but that's that additional stage where you have to try to convince somebody that's been sampled to actually participate. So ideally, you conduct interviews with those sampled individuals, and in NHANES, some individuals are also invited to complete that medical examination. They're invited to go visit that semi-trailer and go through a full medical examination. And that's what's unique about the study. So just as an example, in NHANES 2, there were 25,000 people roughly interviewed about their medical history, and about 20,000 completed medical exams. So that gives rise to the need for 2 different weights in NHANES, right? One weight is going to allow the people who did the medical history interview, we can reflect back to the population based on those respondents. But then some individuals were subsampled for the medical examination. Could have been for cost reasons, or whatever the case may be. That requires a different weight, because they need to speak for the other 5,000 people who weren't subsampled for the medical examination. So as a data analyst, then, you have to take a look at the NHANES documentation and say, oh, wait a minute, there's 2 different weights. And it depends on what variables I want to analyze. If I'm analyzing somebody's blood pressure or their cholesterol from the exam, I need to use that exam weight. But if I only care about the medical history and how many times you've been to the doctor in the past year or whatever, maybe I just need the interview. So it all depends on what variables you want to analyze and reading that documentation. The NHANES documentation talks about all these different weights and when you would use different weights for different variables of interest. Okay? So that's another critical step, is reading that documentation and understanding what weights are available for analysis purposes. This is in the case of the NHANES, but for any study that might have multiple weights, that's why it's so crucial to read that documentation. Okay. Okay, so that's just an example of some essential design features of the NHANES. Questions about that NHANES example or anything else that we've talked about thus far with NHANES? Any questions?
Sorry, got a question.
Yeah. And again, if you could introduce yourself, that'd be good for the people, especially for the people on Zoom.
Okay, my name is Nya, second year PhD candidate at the College of Pharmacy. And my dissertations involve analyzing data with NHATs, but I guess I can learn from the class to work on my project.
Sure, yeah.
So,
You want to spell out NHATS for the rest of the class? You might not be familiar with that acronym.
it stands for National Health and Aging Studies.
Yep.
So,
yeah. So that. Go ahead.
Yes. What were you saying?
I just say NHATS is another example of a probability sample. So she's referring to a probability sample with a complex design. That's one that Michigan actually helps to conduct. So.
Okay, so my question for this slide is, what if we use interview data and exam data at the same time? So which one that we should include now?
Great question. Yep. So suppose you're fitting a regression model, right? Where you want to predict a person's blood pressure with something about their medical history, right? It's kind of a lowest common denominator thing. All you need is one variable from that medical examination to necessitate the use of that exam weight, right? Because the use of that one variable in your analysis is limiting your analytic sample to the individuals who were subsampled for the medical examination. So even though you have a whole bunch of other medical history variables, you're still ultimately analyzing people who were eligible for the actual examination. So in that situation, you would need to use the exam weight.
Thank you.
So you shouldn't use the individual. When you're saying that you should use the exam weight as opposed to using the interview.
Yeah, the exam weight still corresponds to an individual. It's just the weight assigned to those individuals who were subsampled for the exam, right? So when you say, I want to fit a multivariable model just to blood pressure, you're limiting yourself to the 20,000, right? Even though you merge in all that other interview data, you're still limiting yourself to 20,000. So that means you need to use that weight, right? And again, you can see that if somebody was to make the mistake of saying, oh, here's the interview weight, I'm not going to read the documentation because I'm scared of it. I just want to use the interview weight. They'll be putting themselves at risk of bias if those additional weighting adjustments for the subsampling are informative about the variables that they're trying to analyze. They say they oversampled people in worse health or something like that for the medical examination. You put yourself at risk of bias. So it's always important to read that documentation. Question to Jupiter?
Yeah, I think back to the features that you talked about, the complex survey. I'm looking at its stratification, clustering, but also the weights. I'm wondering this example of respondent-driven sampling. I mean, just the word complex, I would think it's a complex, but I don't know whether how it can fit.
Good question. So Jupiter is asking about something called RDS, or respondent-driven sampling. It's a very important data collection technique that Dr. Sung-Hee Lee, who you'll be meeting in the sampling program, has done a lot of research in. Respondent-driven sampling is an example of non-probability sampling, right? Because when you ask individuals who are called seeds that have been sampled, possibly according to probabilities, you're asking them to do their own recruitment of other individuals in their network. So at that point, you relinquish control over probabilities of selection. So you no longer have this entire class of methods at your disposal. So a big area of research is, how can we analyze data from respondent-driven samples and still make inference about finite populations? That's an area where Dr. Lee has done work, her colleagues have done work, but by definition, RDS is non-probability. So we have to think about alternative approaches because we don't have full control over those probabilities that others are invited to participate. That's the issue. It's a great question, though. It is complex. I agree with you. RDS is a very complex procedure, but it's not a probability sample. That's the important thing to recognize. Great questions. Any other questions?
Yes, I have a question going back to the second stage. Basically, you're only sampling at that stage combinations of blocks with at least 200 to 250 people. So, is for the blocks that do exist with a less, in the ultimate weighting procedure, is there an account based on what we estimate that to be that includes that, or do we just assume, or do we just, when we're analyzing this, we should realize that we can't apply these results to a population, you know, or areas with that less that? Do they account for that in the final thing, or is it just no, don't even try to apply it?
Yeah, and usually those estimated sizes, they're assumed to be known, but PPES is a technique that built into that procedure is a way of accounting for those estimated sizes. So when those final probabilities are determined under PPES, the fact that those are estimated gets accounted for as part of that procedure. So in the calculation of the overall probabilities based on those estimated sizes, the fact that those are estimates is accounted for in those ultimate probabilities. Yep. So that's built into the estimation process. For purposes of this class, we just need to be aware that that's built into the probabilities, and we need to use those probabilities for estimation. That's the key.
So we could apply if I use the correct weights, etc. We could apply our estimates to all people within areas of U.S. regardless of the.
Right.
Okay, thank you.
Right. Yep. That's the idea. Those weights are designed to allow researchers to make larger inferential statements about the entire population. Yep, that's correct. And that's why I have colleagues here at the University of Michigan who half of their salary is maintaining weights. A complex probability sample design like this, accounting for all these probabilities, documenting all these probabilities, maintaining those weights, it's a huge job. Especially when you have these kinds of estimated sizes. Where do I get those estimated sizes to begin with? What data source should I use? It's a huge job. And that's why when we do this research and we find that 50% of researchers are completely ignoring the weights, we get a little crazy. It's staggering. Yep, George?
Yeah, I just wanted to ask you, for example, if you have let's say you have a 3-stage sample design, where in the first stage you'll be selecting classes, then household in the second, and maybe individuals in the third. But the second stage requires you to do listing. And listing itself already it's an exercise that is very costly. So what I have seen most people trying to I don't know, in terms of now the weight, if that stage is not done, so if you don't know the probability of selecting a household or in a specific class, for example, how do you account for that? Because what I've seen, they will try to use certain techniques like spinning the bottle.
Right.
So how does that influence?
So, and it's a great question, because especially if you leave your field staff, if you leave it up to them how they go about identifying the households. There's some research on, field staff actually doing the sampling themselves. It's all about whether, as a researcher in charge of that sample design, if again, you're like an RDS, you're relinquishing control over those known probabilities of selection. One thing that's often done in this case is you assume that whatever they're doing, spin the bottle, random walks, etc., whatever they're doing is essentially giving you a simple random sample. But you have to monitor it. Like if some individual is just walking to a neighborhood and they see a whole bunch of dogs out there and they see a whole bunch of safety concerns and they say, I'm only going to visit these 3 households that are closest to me right now, there's nothing random about that. So you have to do whatever you can to ensure that they're doing random objective selection if they haven't been given a set of instructions. So it looks at least something like a simple random sample. More often than not, they're going to be working together with some kind of central guidance to say, okay, here's a map of the area. Here's all the addresses. These are the specific addresses that we want you to visit, period. So you take that control out of their hands. But if you're unable to do that and you say, okay, give me a random sample of households, you at least need to have somebody accompany them for a subsample of that process, or some way of monitoring to make sure that they're doing random selection. Because what you'll have to do in most cases is assume simple random sampling. But if they're only picking the biggest houses or the safest houses, or whatever the case may be, and they're doing that over and over and over again, you could be introducing a whole lot of bias in your sample that's not being accounted for. So it's tricky, but it requires a lot of monitoring. And that's what Ramiro is going to be talking about. And his guess is how to monitor the data collection process. Kurt?
Yeah, I just want to add, like, sometimes to control, I've seen some surveys that we use mobiles. So if there is like list of households, so the interviewer can have listed the questionnaire only after he reaches that household.
Right.
Otherwise, the mobile is not open.
Exactly.
Yeah.
That's one kind of built-in control, George, is that, you know, they say, what's the address? And they say 163042 Linscomb. And they don't even have the ability to enter any information because that wasn't part of the actual sample, right? That's one example of this kind of monitoring. But you try to institute whatever you can to prevent them from making non-random selections because you break that probability. There's nothing worse than having this kind of multi-stage design, and at some point in that process, an individual goes rogue and they break your probabilities of selection.
But at that stage, then you have already done the listing.
You've done the listing.
Yeah, I think
No,
what he was talking about, they don't have,
There's no listing.
you have not.
Yeah, that's where you have to assume that they're doing a random, they're hitting every fifth house in their walk or whatever the case. You have to give them instructions in the absence of a list to produce something that looks like a random sample, right? And that's a challenge. It's a notable challenge.
Right, so you must have a supervisor.
Oh, yeah. Yeah, this training, supervision, monitoring, that's why I said a buddy system.
Yeah.
Where two people go out and do it and like independently replicate each other's work, something like that. To prevent that case where your entire field staff is, you know, systematically only visiting the biggest houses or something like that.
Yeah, but so you have and system to check if there is a systematic choice or not.
Yeah, that's the challenge. So how do you verify that a random walk is actually
Yeah.
random?
Yeah.
It's a challenge. And that's something that the people managing that kind of survey have to think about. How are we going to validate that they're actually producing a random sample of households from that neighborhood?
Yeah, because I imagine that it's very difficult to detect this kind of
Sure.
systematic bias.
Well, you can look at the characteristics of the households that they're recruiting, right? You can see like sizes, whatever. You know, there are ways to look into it, but it's that's why monitoring of this entire process is so very important. Yep. Okay. All right. So we've reached noon. So I think we're going to call a stop here. When we come back on Wednesday, we're going to talk about different types of combinations of sampling plans and then analytic approaches that you might use. So this is where we're going to talk about design-based versus model-based inference. And then on Wednesday, we're going to talk more about the details of stratification, cluster sampling, and weighting, and why it's so important to account for all those features via what are called design effects. So we're going to introduce this notion of a design effect in addition to talking about the origins of weights and so forth on Wednesday. Okay. Okay, so any other questions though before we close for this morning? Any other questions yet? Yeah, go ahead.
So in third stage, we are selecting households units. So how many households are these selected in Inference and what kind of subject?
Yeah, so usually NHANES will sample about 15 to 20 big areas in the US. So, you know, it's a challenge there of like, how do you draw a good representative, Raphael hates that word, but representative probability sample of areas in the US. Then once they go to those areas, they'll usually select 200 to 300 households to invite. So it's a heavily clustered sample where there are big sample sizes within each of those areas. Typical NHANES data set, you're going to have between 5,000 and 10,000 respondents, again, that combined to your sample. So it's not what we would call big data by any means, right? It's not there's not 50,000, 100,000 people in these samples because those medical examination data collections are so expensive. You just can't, have doctors work with that many people. So I just got invited onto an NHANES kind of task force panel to rethink its entire design, just because it's become so expensive. So I'm interested to see like what kind of questions they have about that. But yeah, you're usually going to see 5,000 to 10,000 people in a given data set, about 300 people per area, something like that across the 2-year cycle.
So this design is basically based on the individuals, not on the household.
Yeah, it's all about an individual's health. That's right. Unlike a study like the health and retirement study, where you may want to ask somebody about the total household income or the total household assets or something like that. NHANES is all about what's your individual blood pressure, what's your individual weight. It's all about the individual. Yeah.
And the samples are being drawn on the randomly basis, or?
Oh yeah, everything, probability samples, everything is random. At no point is there any kind of subjective selection of individuals. Everything we've been talking about today, the sampling is entirely done at random, according to those predefined probabilities. These things like RDS, random walks, that's where we put the probability sample at risk and introduce a level of subjectivity. We want to do everything we can to make it objective at all these stages relative to the probabilities. George?
Yes, question with regards to border surveys or tourism surveys.
Yeah.
Where, for example, you want to maybe inbound survey. How does one ensure the randomness? Because
Well,
I mean, first to start, you don't even have a list of your.
yeah, you don't have a denominator.
Yes,
Right.
so I was wondering, because we have such surveys running in Namibia, but we have other reporting, but when they say that they do weights, I mean, how do you talk about weights?
Yeah, you have to make an assumption about that denominator. Like it might be the average number of people visiting over a certain period of time. And then you try to take 1 out of every 100 or whatever to give them the survey. You do something systematic like that. You have to make some kind of assumption about the size of that denominator. Otherwise, you're again in non-probability world. And it's a huge area of research right now, is because so many of these different samples are non-probability samples. What can we do to make inference based on those non-probability samples? And sure enough, all the different techniques that people talk about involve combining a non-probability sample with a probability sample. It can be matched on a number of common variables. All of those techniques start with that kind of linking of data from a given non-probability sample with some other big probability sample, government sponsored, to try to understand, if I had combined these two as representing some larger population, what was the probability of being selected for that non-probability sample? You try to infer what their weight would have been had they been part of that probability sample. So there's a huge literature on all that kind of stuff with non-probability sampling right now. And if any of you are working, in that particular area, I can point you to references, because I'm working on a bunch of projects right now that are working on, what to do in these areas. And there's now software starting to emerge for how to apply these techniques for non-probability samples. So, but unless you can make very strong assumptions, like in that example about a denominator, like I was saying, it's very difficult to put down any kind of probabilities that are defensible. It's a challenge. It's a huge challenge.
Oh, this is Sarah again. I might need to send one, because I'm actually PhD graduated about 8 years ago, research at USDA, and the main reason I'm interested in surveys, I'm working with a joint sample of the ARMS, a large complex agricultural survey, and then also looking at our administrative data, kind of taking a subsample of ARMS that are in our administrative and working with that. So exactly the area that I'm struggling on. So trying to take administrative small sample and combine with those identified in a larger complex sample and try to draw inferences for data items we are missing in our small administrative data that's in the larger complex.
Yeah. So Sarah, it all depends on any kind of selection that you're doing. Like, are you actually drawing a simple random sample, or is there a subjective element to it?
I mean, the data we have is conducted by NAT, so it takes the complex sample, and that's a separate one. we've gotten data linkages that we've been provided in a secure environment, data linkages that take our administrative data, which is everything on those within our programs, and being able to link those to those who have responded and filled out and then of this survey by year. So it's kind of like a subset of this complex sample that doesn't fully we have, but doesn't look at everything they have.
Yep. So one of the things we'll talk about over the next couple of weeks is the idea of subpopulation analysis. So you could think of the people who are, able to have records successfully linked as being a subpopulation of the larger overall target population. You could still use design-based methods with those weights, but we're going to talk about some of the important considerations when you're dealing with a subpopulation like that. And just to kind of preview, you never want to delete all the other cases that weren't successfully linked. You want to read in the entire sample that could have been linked in theory. You never want to physically delete the cases that are not in that subpopulation that was successfully linked. We'll talk about reasons for why that is, but yeah, you can still use design-based methods in that case, assuming that all the cases that could have been linked had probabilities of selection to start with.
Okay.
Yep. Yeah. So we're going to spend a lot of time talking about subpop analysis for sure. Okay. Great questions today. Any other questions for now? Okay. If not, we'll pick back up with slide 15 here. We'll get into module 2. Remember, on Wednesday, we're going to introduce homework number 1, and then we'll introduce the course projects as well moving forward. So, okay. All right. Thanks, everybody. We will see you on Wednesday. Thank you.
Just little announcements for the people here at the Symphony program. For those who are Leslie Kish fellows, like please see Elizabeth here. She's going to work with you like on the Leslie Kish fellowships. Again, there's some brochures just by the door there, and like some informational sheets here. Make sure that you get those. And we'll be back at the same room here at 2 o'clock. Okay, so I have like a little bit less than 2 hours for lunch. If you go here to, if you haven't walk around, to go like over.
How about now? Are they showing up now?
Yes.
Okay.
Yeah.
Okay, sorry about that. Yeah. So we're talking through the first 4 parts of homework assignment number 1, which is up on Canvas. Okay, sorry about that. So that's just I'm just getting the sequence of buttons down for the display this time around. So okay. Okay, so then part D says provide a reference for the documentation for your survey data set. So like we talked about on Monday, okay, essential to review the documentation for a given data set that you'll be working with. So for part D, this could be a web link. It could be a citation. It's something where Young Chow and I can take a look at that web link and see the same information that you're seeing about the data set that you want to work with. And if it's a data set that's being prepared at work or something like that, you're not allowed to share any documentation at this point, that's fine. Just provide a little summary of where we might find the documentation eventually. Okay, so that's the second part. And again, team submission. These homework exercises, there's going to be a part in each one that helps you work toward the milestones for submitting the final project. So a lot of what you're identifying here is going to go toward defining your data and methods section in the final project. Okay, and then part 3, another concept that we're going to talk about today is power analysis. It says many standard power analysis procedures are based on an assumption of IID simple random sampling. Okay. So when you use a power analysis calculator, you're trying to do sample size calculations, and you have an effect size in mind, or you want to be able to compute a confidence interval of a certain width, that all assumes that you're dealing with IID data. And we're going to talk about how to adjust that today for dealing with complex samples. So when you're doing power analysis for these kinds of complex samples, you need to account for those complex sample design effects when you're performing those calculations. We're going to learn about a concept called the effective sample size today, which is the size of a simple random sample that would give you the same amount of precision as your complex sample. Okay? And that's the calculation that we need to input for these kinds of power analysis procedures. So the problem says, a data producer has performed many descriptive analyses of an existing survey data set, computing standard errors that take the complex sample design into account in each case. Suppose that the documentation for that data set says that the average ratio of the complex sample standard error to the simple random sample standard error is 1.5. And the actual size of the sample for the survey data set is 5,000. What would be the effective sample size that you would use for power calculations? Okay, you don't know what that means yet, so don't worry about it. We're going to talk about it today. But this is crucial when you're proposing studies or you're planning studies that will involve secondary analyses. If you have a data set that looks like it has 20,000 observations, you look at that and you say, wow, that's great. Okay, I have 20,000 observations. I'm going to have more than enough power to pick up whatever relationships I want, or my confidence intervals are all going to be super narrow. But the actual effective sample size associated with that data set may be much, much lower. And that's the quantity that you need to use for power analysis. It's one of the key takeaway points from today's lectures. Okay, so we'll come back to that during the lecture today, but that's the third problem. Okay, so just those three problems: getting familiar with the ESS data set and its design features, thinking about the data set for your final project and its underlying design features, and then doing this power analysis calculation given the information provided. Okay, so that's what's going to be due on Monday. Remember that you can work together as a group on the homework assignments, but ultimately you need to submit your own version of each homework assignment, and that can be done via the Canvas assignments tab. So you would submit your assignments via the assignments tab. That way Youngchow and I can document what assignments have come in, when they came in, and so forth. And we'll probably end up giving you feedback via Canvas as well. Okay, so we'll give you comments and marks in Canvas. Okay, so let me pause for a second. Any questions about homework assignment number 1? Any questions about the first assignment? Yeah.
So that electronically or it will be submitted
Via Canvas. Yeah. So in the assignments tool, you'll have the option to submit a file containing your final work, and that's where you would submit the assignment. Yep. Other questions about homework assignment 1? Okay, definitely send an email if anything is unclear as you're starting to look at that homework. Okay, turning then to the final course project. This documentation is also available on Canvas under the final project folder. You'll see ServMath 614 final project. That's where this PDF file is. I also want to point out that in the final project folder, you see 4 different examples of papers that were previously receiving A grades in this class. Okay, so you can take a look at those PDF files, get a sense of what expectations are for a high quality final project, what the structure of the papers would look like, and so forth. These are all real papers that have been written by real participants in this class in prior years. Okay, so that's designed just to give you a flavor for what these final projects will look like and the kind of work that you have ahead of you. Okay. Also, there's this article by my good friend and colleague, Sean McCabe, and a couple other colleagues from 2013 that gives you a sense of what a peer-reviewed journal article presenting a secondary analysis of survey data would look like. How you describe the sample, how you describe the analysis methods. I just picked this out because I think it's a good template for how you would go about talking about the importance of accounting for these kinds of features in a real survey analysis. And so, like I said on Monday, what is done there is what we wish all of the peer-reviewed articles would do, basically. But unfortunately, many of them do not. Okay, so that'll give you a sense of what an actual peer-reviewed publication might look like. So altogether, these are to give you an idea of what we're looking for in that final paper. Okay, so back to this PDF document. So the final project, again, is due on July 26th at 5 p.m. We are considering that a hard deadline because it is the end of the Summer Institute. Okay, so we don't want to go too much farther. People are going to be leaving. That's really considered a hard deadline. But if you do need an exception for whatever reason, just reach out and clarify why you need the exception, and we can discuss that. Okay. So final project, again, you can work as a team. Could be 2 to 4 participants. Could be more, just depending on what you guys are thinking about. Just keep in touch with me about your ideas and your thinking in that case. Some of you have asked me if you can do the final project solo. That's fine, but you're at a bit of a disadvantage relative to teams that might be working together. We do only have 8 weeks. I've mentioned some of that to some of you over email for writing an entire paper by yourself. So it's a lot, but if you do want to do that and you have the ability to take that on at this point, that's a fine option as well. Okay, just again, making sure everybody's aware of what they're getting into. The goal of the final project is to demonstrate that you've mastered the core material of what we're talking about in this particular analysis course. And that includes talking about the sample design features, talking about the weighting that's associated with these survey data sets, all these design features that affect your estimation and inference, and demonstrating that you can correctly use the specialized software procedures that we're going to be going over to do analyses of the survey data on your own. Okay, so it's a combination of writing about the analysis approach and the methods and your results, and then demonstrating that you can write code on your own and execute these analyses in a correct fashion. That's really the goal of the overall exercise. And as a team or an individual, you're going to have freedom to choose whatever data set you want, whatever kind of analysis you want, as long as it comes from a probability sample with the design features that we're talking about. And I'm more than happy to communicate with you about options, ideas that you're thinking about in terms of these data sets. Feel free to reach out and ask me if you have any questions. Okay, so again, you're strongly encouraged to identify an original data set that you're working with, that you're familiar with. If you don't have a data set of your own, you're welcome to choose one from the course data sets. That's perfectly fine, entirely up to you. The course data sets have just been sanitized to some extent. Like you're only going to see a small number of variables. And so for each of the data sets in the course, there are much more variables. There are many more variables available online. If you were to look at public use versions of these data sets and you have interest in other topics, you're more than welcome to look at larger versions of the data sets if you would like. Okay? And we have links to more information about the project details at the ASDA website. Okay, so key kind of milestones in terms of the overall final project. On June 17th, which is 2 Mondays from now, that's when the project prospectus is going to be due. And as I mentioned on Monday, that's a 1-paragraph description. Really want to highlight 1 paragraph. Do not write a paper for June 17th. Okay, Young Chow and I are not in the mode where we want to read papers at this point. We're only asking for a paragraph. That's all you need to do. Don't overdo it. Okay. That's just going to describe the data set that you want to work with and the objectives of your proposed analysis. That's it. And at that point, we want to know just who the team members are on a given team. Okay? Don't overdo it. Don't overthink it. June 28th, that's when you're going to submit drafts of your introduction. Okay, briefly introducing your research question, maybe a little bit of background literature. We'll talk about that. And the design and methods. So that's where we want you to have thought about what kind of analysis methods you want to use, like the answer to question 2 on homework number 1, talking about the features of your complex sample design, writing that all up in the format that you see in those example papers on Canvas. July 15th, that's when the preliminary draft of the final project is going to be due, now including all of your results and your discussion of those results. And that's just a draft, so it doesn't have to be perfect, but Young Chow and I are going to be giving you feedback on those submitted drafts and saying, here's what we'd like you to focus on over the next couple of weeks as you lead to the submission of the ultimate final project. Okay, so we're going to really act like advisors on those drafts and provide you with feedback based on what you have there. And then again, July 26th, the final project paper is due by email. Okay. Any questions about that timeline? That clear to everybody? Okay, so your final project can employ any of the analysis methods. You don't have to fit a regression model. The final project could be entirely descriptive, if that's what you want to do. It is entirely up to you. If your objective is to estimate a proportion, to answer a research question, write a final project that estimates a proportion. You have complete flexibility. It doesn't have to be complicated. We just want you to demonstrate that you can write about these kinds of analyses and use the software appropriately. That's the whole exercise. Okay. All the analyses should incorporate the appropriate survey weights. All standard errors should be adjusted for the design features that we're talking about. You can use whatever software you would like. Okay. And a lot of people in the past, they've created an appendix that contains their code. think it's a good idea. More and more journal articles are asking for this when you submit journal articles, like providing your code, making your code available. Plus, it's something that you can look back on. So if you want to repeat the analyses that you've worked on this summer for some other project, you can go back to that code and just modify it for the different kind of analysis that you're working on. So I think it's a good idea just to document that as well. Okay. So the final report itself is going to be 8 to 12 pages, double spaced, and that includes figures and tables. So it does not need to be excessively wordy. We just want you to demonstrate exactly what we're talking about in this class. Past years, we've received 70-page papers. Don't do that. I'm just going to send it back and say, give me 12 pages, not 70. Okay? There's no need to be verbose, to go on and on and on. Your introductions don't need to present 45 research articles motivating your analysis. This is just an exercise in performing this kind of analysis. Okay, so 8 to 12 pages, double spaced, including figures and tables. Okay, it can be in Word or PDF format. If you submit it by email, that's fine. And then your final grade for the team is going to be based on that overall report. So the basic outline of the project, you're going to start with an introduction. That introduction can cite a couple of articles, a couple of previous technical reports motivating your research question, and then explicitly stating your research question and the target population that you're interested in. Okay, so that's a key point. I want to be able to make inference about target population X with this particular analysis. So who's the focus of your research here? Then a data and method section. That's where you talk about your data source. You talk about the features of the complex sample design that you need to account for, and then the analysis techniques that you want to use. Also a good idea in that section to lay out the specific variables that you want to work with, that you've picked in your data set that you want to work with, saying what they're measuring, how they're measured, and so forth, so that the data that you're using are very clearly described. Okay. Then section 3 is presenting your results. Okay, so what were the actual estimates that you computed? What do they mean? How do you interpret them in the context of your larger target population? Key thing about the results should be a robotic presentation of the results. This is my estimate. This is how I interpret it. Okay. The results section should not go into extensive discussions of what the results mean for the larger population, what the implications of those findings are, just a robotic presentation of the estimates and their interpretations. Okay, so keep it simple. The results section. Then the discussion, that's where you can go into more detail. Not just reiterate your results, but say, here's what these results really mean for my target population. Okay, maybe people thought that a certain characteristic was not that prevalent. Turns out it really is, based on this data set, something like that. And what does that mean for public health? Or what does that mean for, you know, social advancement, or whatever the case may be, whatever your research objective was? Discussion is where you can go into more detail about the implications of the results. Okay? And then any references that you cited as a part of that introduction or the results or the discussion or anything like that, just documenting citations for those references in conclusion. Okay. So that's the basic structure. You can certainly modify that as you please. Again, we'll give you feedback on the drafts multiple times over the course of these 8 weeks, so you'll have an idea of what's going on, but that's the basic structure that we're looking for. Okay. So the final project is going to be graded out of 50 points, and these are the key elements that we're going to be looking for. Creativity. Okay, so you've thought about an original research question, something important to you and your team. You've identified a unique survey data set, and you've thought about an interesting research problem to look at. Being concise but thorough in presenting your method, your results, the problem, and so forth in your writing. Again, 8 to 12 pages. The quality of the overall presentation, nicely formed tables, any figures that you might be using, carefully put together, clear that you spend some good time thinking about your analysis. And then the strength of your discussion and interpretation of the results. Okay, we want you to try to use good English grammar. Okay, this is to be written in English. Okay, do your best at that. Okay, not a big deal if there are issues there, but we want you to do your best in trying to write a quality report. Because like I said, a lot of papers that have come from this class do eventually get published. So it's a good idea to think about this exercise. You know, start as if you're going to be submitting this to a journal down the road. Have that in your mindset with the article that you're producing. Okay, now one point that I want to make that's not common to other kinds of scientific papers is that the final project report should include a discussion of estimated design effects. for key statistics. Again, we haven't talked about that yet. We're going to talk about it today. But in addition to all your estimates, we want you to supplement those estimates with estimated design effects for each of the different estimates that you're providing as a part of the results. Okay, again, we'll talk about what that means, so don't worry about that. But I want to emphasize it here. Typically, you would not be including design effects in these kinds of secondary analyses, but for the purposes of this class, we want you to report those design effects and then interpret them as well. Okay, so that's just specific to this particular project. And again, you'll see examples of how that's been done in those papers that are up and available on Canvas. Okay. Okay, so that's the final project. Again, we'll keep talking about this as we go over the next 8 weeks, but are there any immediate questions about the logistics of the final project? Any questions about this?
So, as you said that you have to work in groups.
You don't have to, but it's advised.
Okay.
Yeah.
I was wondering that basically that means we have to agree on a data set.
Right.
And, but then we write separately. That's what you don't write.
No, yeah, the final project is a group project. So your team will only be submitting one project. This is unlike the homework exercise. The homework exercises, you have to submit those individually. You can work on them together, but each individual student needs to submit the homework exercise on their own. The final project, you are submitting a single final project as a team. So the team will get the same grade on that project. Okay. Thanks for clarifying that. Other questions about the project? Any Zoom questions about the final project?
Yes. Hello, good morning, sir. Good morning, colleagues. Yes. Okay. So my question re the project is normally when there is like well, it sounds really good in terms of, you know, that it could be published and so forth. Or it will be at that level where we can publish it at the end of this course, or, you know, or develop it. Great. I was just wondering, within the context of the course, is there going to be, you know, like in a PhD program, for example, you normally have a direct supervisor that works and guides you. Is that the role that you would play in terms of?
Yeah, so I will be providing, I'll be providing consulting and advice as you continue to work on. So it says that up here in the project. The instructor is prepared to consult with your team on the project, but their role will be very much like that of a statistical or technical advisor. Okay.
Okay, great, great. Thank
you. Yeah, so you're welcome to ask questions. You know, you're welcome to seek feedback as you're working through that project, but I will be giving you advice. I won't be literally writing paragraphs with you, right? It's an exercise on your own and with your team. But I'll be giving you overall kind of overarching advice on the approaches that you're taking and so forth. So we don't have enough people to match up with 35 students at this point, like you would in a PhD program, but you're welcome to meet individually with us and we'll give you guidance about the structure of the overall report. But it won't be as in-depth of an interaction with the instructor as you would see in a PhD program or something like that.
Okay, thank you. Thank you very much.
Yep, good question. Other questions?
Quick question.
Yes, sir.
The data set I'm hoping to use that is part of my current work employment project is within a secure environment, ADRF. It's basically, I can't share within the environment any of the actual microdata, et cetera, just results.
Right.
That's be a problem, right, for using it for this one if I
No, because you're never going to be asked to share microdata or anything like that, but it might cause some issues with sharing documentation. It shouldn't prevent you from writing about the variables that you want to work with, writing about the sample design, you know, communicating results. The one issue I could see is if you need to get approval or release of output from analyses that were performed within a restricted environment, and you can't actually include tables of results or anything like that, you know, without getting that prior approval. If that's going to cause an issue, you probably want to talk to the coordinators of that restricted data enclave and clarify the timeline of the course that you're in right now and say, these are the analyses I want to do. And, obviously I would need to see these by, beginning of July or something like that to have sufficient time to write up that final project. I would just try to establish an understanding with the coordinators of that enclave about that timeline. So.
Okay, that would make sense, but I'll just need for example, I would need my estimated variables, standard errors, the usual things, that would be the end thing that you'd want to see, right?
Right. Exactly. We're just looking for tables of aggregate estimates in the final projects, but I'm on projects here at Michigan right now where I can't even release those.
Yeah.
So that's what I'm saying. If you need to get approval of generating and producing aggregate estimates, it's better to start that process literally today than to wait until July 15th and they say, well, we're not going to give you that output till August 21st. Right? Yeah. That would be a problem. So, yeah.
Understandable. We have our 30+ days to decide when we'd like to review and release. Yeah.
Yep.
Okay, thank you.
Okay, thanks. Any other Zoom questions about the project? Okay. Sounds good. All right. So again, please email if anything's unclear about the homework or the final project. Okay, so we're going to get back into our discussion of the basic concepts from Monday. And today we're going to talk about complex sample design features and also weighting. We're going to spend a lot of time talking about weighting and the implications of weighting for the estimates that you produce and really where weights come from in the first place. Okay, so we talked about some of the basic ideas of complex samples on Monday, and there's this nice table in this paper by Hansen and colleagues in 1983. And I really like this paper because it does a great job of explaining the differences very clearly, very readable fashion for people who may not be survey statisticians. It does a great job of explaining the differences between design-based and model-based approaches. So we're primarily going to be focusing on design-based analysis approaches in this particular course, but there's a very nice description of the differences within that particular paper. And they have this table where you can basically combine a sampling plan with a method of inference in terms of the overall approach that you use for making inferences about a finite population. And as I kind of boldface and highlight here, this course is primarily focused on probability samples where we're using design-based analysis approaches to make inference. But this is not to say that that's the only way that you can analyze survey data. That's the message that I want to make clear at this point. It's perfectly acceptable to take model-based approaches, and we'll talk about what that means, as long as you can justify the models that you're using to analyze the survey data and make sure that you're not generating biased estimates with the approach that you're using. So our primary focus is going to be on probability samples, but there are many other ways to draw samples, including model-dependent sampling. Okay, but that's not going to be the primary focus of our course here. So overall, Hansen and colleagues talk about the idea of a sample design as pairing a sampling plan with an estimation and inference plan. Okay, so that's like the overall sample design. So a key point here is that when you're sitting down to analyze the data, you never want to make up features of the sample design on your own. This is always prescribed when the sample is selected. This pairing of the sampling plan and the estimation and inference approach that one would use to make inference about the finite population. Okay, these are always defined in advance as a part of the overall sampling design. Okay, so what that means is when you're sitting down and analyze the data, you don't want to say things, well, I'm going to treat gender as the stratifying variable, or I'm going to treat this variable as the clustering variable, or I'm going to make up my own weight and then use that weight for the analyses. Never wanted to get into that. Okay, all of these design variables are prepared for you in advance as a part of the overall sampling design. And that's why the documentation is important, because that documentation says, here are the variables that you need to work with when you're making finite population inferences. You never want to invent these design variables. They're provided for you by the data producer. Okay? So I see that a lot, okay, in consulting, where people are like, well, I really want to break my analysis down by racial and ethnic groups. So I'm going to treat that as my stratum variable for my variance estimation. That couldn't be farther from the idea. okay? We want to use features of the sample design that were developed for you by the data producer when you're doing these overall analyses, okay? So our focus is going to be on design-based approaches, which we'll define in a second, but there are alternatives. And when we talk about multi-level modeling later on in the course, we're going to get into alternative model-based approaches that one could use to analyze survey data. Okay, but our primary focus to start with is going to be on these design-based approaches. There's actually a ton of research going on as we speak about Bayesian approaches to the analysis of survey data, which are largely model-based. And some of you may have heard of Bayesian analysis in prior courses, but that's a very active area of research in the world of complex samples right now, is how to take Bayesian approaches to the analysis of survey data. And people are starting to demonstrate the benefits of model-based Bayesian approaches. So if we have time, we'll touch on that a little bit as well. But we're really focusing on introducing the tried and true design-based approaches to making finite population inference in the course. Okay, so what exactly do we mean by this distinction? If you take a model-based approach to the analysis of survey data, which is really what you've been doing in all of your intro stats courses, all of those, the introductory stats courses that you've taken present model-based approaches. That's really the way to think about it. And the idea is you assume that the variables in your data set are governed by a probability model. The values on those variables arise from a probability model, and you try to fit that model to the data set that you're working with. So for example, you might assume that the measures on Y are independent observations from a normal distribution with some mean mu and some variance sigma squared. We joked about S squared, okay, right? But that's the idea here, okay? You're saying that this particular variable in this particular data set follows this probability model, and my analysis goal is to estimate the parameters of that model. Okay, estimate the parameters of the model that generated the data that I see in front of me. That's the idea of model-based analysis. Okay, suppose you have a binary variable. Okay, you assume that that variable follows a Bernoulli distribution, and your goal is to estimate the probability that governs that Bernoulli distribution. What's the probability of getting heads or tails in a coin flip? What's the probability that someone's going to get a particular disease? Okay, you assume a probability distribution and you estimate the parameters of that distribution. Model-based approaches assume no finite limit to the process that generates the values that you see in your data set. Okay? So model-based approaches don't care about the concept of a finite population. Model-based approaches say, you have a set of data, the values on that variable came from a particular model, and you want to estimate the parameters of that model. That's it. It's an infinite data generating process. Like you turn the crank, you spit out data. And the parameters govern how that crank works in spitting out the data. An infinite process. There's no concept of a finite population in model-based approaches. So everything in your analysis, your estimators, your hypothesis tests, your confidence intervals, everything is governed by the probability model that you assume for a given variable. Okay? So it puts a lot of pressure on you as the analyst to get that probability model right. Okay? Otherwise, all the stuff here, your hypothesis tests, your confidence intervals, etc., those may be incorrect, or they may be underpowered, or they may be biased. Like if you leave a variable out of a regression model, omitted variable bias, everything depends on the model that you specify for your variables of interest. So model-based approaches can be very powerful, very efficient if your model is correct. And here's just an example of this kind of model from a natural law, right? A lot of the physical sciences are governed by these natural relationships between variables. If that's the right model for the data that you're looking at, that's great. You're gonna have highly efficient inferences, everything's gonna look great. But if you get that model wrong, model-based approaches can really break down. Okay? So that's the idea here of a model-based approach. Now, Neyman's 1934 paper that we talked about on Monday presented a completely different inferential framework, with the goal being to make inferences about finite populations. Populations that in theory you could go out if you had the resources, you could enumerate everybody in that population and calculate the values of the population parameters that you're interested in. Neyman laid out a general approach for drawing probability samples and then making inference about some parameter of interest based on the idea of repeated sampling. Okay? where all of your inference is governed by the sampling distribution of a given estimate that you want to compute. Not a model, but the sampling distribution. What does that sampling distribution look like across repeated samples? And I underline that in this original quote from the paper. Given a hypothetical population, find the distribution of certain characters in repeated samples. What Naaman was saying is, if we were to go out and draw thousands and thousands of samples using the exact same probability sampling design, what would the distribution of estimates look like? For something of interest, the character might be a mean, or a proportion, or a regression coefficient, or an odds ratio, or whatever it is that you want to look at as part of your analysis. That's what Naaman was referring to. What's the distribution of those estimates going to look like under repeated samples from the same probability sampling design? And inference is based on that sampling distribution and entirely governed by the features of the sample design, not the model, the features of the sample design. That's the critical difference here. Okay. So Naaman's paper really laid the groundwork for what we refer to as design-based inference from sample surveys. So the goal is to make inference about some parameter, very much like the model-based approach, but in a finite population. We're no longer talking about some infinite data generating process. We're talking about a finite population that we could go out and enumerate if we had the resources to do so. Okay, so we have a target, and that's the focus of our inference. And the inference is all based on the expected distribution of the sample estimates from repeated sampling, not based on probability models. Okay, that's the crucial difference between these approaches. So the design of the sample entirely governs what that sampling distribution looks like. We'll see a simulation showing that here in a second. So typically, design-based inference relies on a confidence interval approach to making inference about that parameter theta. And you see here the three key pieces of this confidence interval, and the course is really focused on how to compute each of these three pieces that allow you to make inference about a finite population. First, you need a weighted estimate of whatever your parameter is. Mean, total, proportion, quantile, regression coefficient. Theta could be any of those things. We need a weighted estimate, okay, where that weight reflects the probability of selection in addition to some other adjustments that we'll talk about. Second piece is a critical t-value that defines the confidence interval. And what's unique about that critical t-value for complex samples is the DF calculation, the degrees of freedom calculation. Complex sample designs yield far fewer degrees of freedom than simple random samples for variance estimation. So that DF is going to be much smaller than what you learn about in introductory stats classes. That's another key adjustment that we need to make in forming these intervals. Then finally, the estimated standard error of that weighted estimate. Okay, that standard error is the standard deviation of the sampling distribution. Okay, so if we had the ability to draw thousands of samples, compute our estimate of interest for each sample, and then plot all those estimates, the standard deviation of those estimates from those thousands of samples is your standard error. And that's the beauty of the approach that Naaman laid out. He said, we can compute an unbiased estimate of that standard deviation based on just one probability sample. The whole idea of having a measurable sample design lets us estimate that standard error, not from drawing thousands of samples, but just from drawing one. That's the beauty of the whole approach. Okay, so we don't need to go out and draw those thousands of samples for the design-based inference approach to work in practice. We can estimate that standard deviation based on one sample. We just have to compute the right estimate of that standard deviation that reflects the sample design features. That's the critical thing. Okay. Once we have all three of those pieces, we can form the confidence interval just like you've learned about in introductory statistics. Okay. The actual calculation, no different from what you've learned about previously with confidence intervals. The pieces are what change, reflecting the features of a probability sample design. Okay. So really the course is going to talk about how to get each of these different pieces. And then the software makes it extremely simple to compute these pieces and then make appropriate inference based on those pieces. Okay, so that's the whole design-based idea, entirely governed by the probability sample design, the probabilities of selection, and then the sampling distribution. That's what we're trying to estimate. Now, we'll talk about weights today, but a key point about working with weights, see if I can draw this here. The key point of working with weights, suppose that I was interested in estimating a mean. Like that was my finite population parameter that I want to look at. Okay. One analysis approach that uses the weights, these weights reflecting probabilities of selection, will result in a sampling distribution that is centered, sorry, but a sampling distribution of estimates that is centered at that population parameter that we're interested in. If you use the weights for your analysis, that will give the sampling distribution that nice property that it's centered at the population parameter. So the average of your estimates will be the population parameter. That's what we mean by unbiased estimation. The sampling distribution is centered at that finite population parameter. The naive analyses that I was introducing on Monday, where people just say, I don't understand the weights, I'm going to ignore it and do my analysis. The risk that you run is that the sampling distribution there is going to be shifted away from that true population parameter. Okay? And the average of the weighted estimates and repeated sampling that you would want to compute if you're ignoring the weights, you run the risk of being shifted away from that true population parameter. That's what we mean by the risk of biased estimates. You're not using the weights in estimation. You're shifting that sampling distribution away from the true population parameter that you're really interested in. So using these probability sampling weights in the analysis gives us this nice property that the sampling distribution will be centered at what we're trying to estimate. That's what we mean by unbiased estimation. Okay? And that's why it's so crucial to use the weights. Okay? So I'll keep coming back to that point as we go through here. Okay. All right, so here is a simulation that shows what I mean by sampling distributions, okay, across repeated samples. Again, back to Naaman's idea. What you see in this picture, let me go back to my pen. What you see in this picture are 9 different scenarios. Okay, those are 9 different plots that you're looking at with different sample designs. So the rows of these graphs are defined by the size of the sample. Okay, we see 500, 1,000, and 5,000. Those are different choices for the design of the sample, how many people we're actually going to sample. Columns are defined by different sampling plans. First, simple random sampling. Okay. Second, selection of clusters where there are 10 elements sampled from each of the different clusters. Third, sampling of clusters where there are 50 elements sampled from each of the different clusters. And all 3 of those different plans lead to a sample of 500 or a sample of 1,000 or a sample of 5,000, right? So if each cluster is of size 50, right, we need fewer clusters. If each cluster is of size 10, we're going to sample more clusters. That's the trade-off. Okay? Now look at what happens in each of these plots. We drew 1,000 samples, okay? And for each of those samples under that design, we computed an estimate of a mean. These data were simulated from a population where the mean of the variable of interest was 25. Okay, that was set by design. This was a simulation study. And we drew samples from that population and calculated the mean for each of those samples and plotted those estimates. So this is a histogram of estimates. It's not a histogram of values on a variable of interest, but a histogram of estimates across those 1,000 samples. That's a sampling distribution. The distribution of the estimates that you would see across all of these 1,000 hypothetical samples. Again, nothing we're going to do in practice, but this is the theory of the design-based approach. The first thing I want you to know is that every single one of these sampling distributions is centered at 25. Okay? Yes. All of these approaches are going to give us unbiased estimates. Any one estimate might be 27, might be 23, might be 24.2. That's based on your one sample. But using the weights gives you that protection that the distribution itself is going to be centered at the population value. On average, our estimates are going to be equal to what we're looking for. Okay, so that's not to say that you're going to get the same value if you go out and do the same sampling again. But on average, in expectation, our weighted estimate is going to be equal to that true parameter, unbiased estimation. So all 9 of them are centered at 25. If you look at that x-axis scale, all these are unbiased. What differs across the scenarios is the variability of the estimate, right? So start with our sample of size 500. Here's what the distribution looks like, centered at the mean of 25, but look at the standard deviation of those estimates. It's 2.81 under simple random sampling, okay? As we introduce cluster sampling with more clusters, look what happens to the distribution. It spreads out, becomes wider, becomes fatter, however you want to refer to it. But the standard deviation of the estimates goes from 2.8 to 4.6. Same sample size. Okay, cluster sampling is making our estimates more variable. Standard deviation gets larger. That standard deviation is the standard error. So as soon as we introduce cluster sampling, our standard error goes up. Still an unbiased estimate, but a less precise estimate. More variability. Okay, that's the choice where we have 50 clusters of size 10 each. Okay, now we shift to a completely different sample design, same sample size, different sample design. Okay, 50 people selected from each of 10 clusters. In the case of 500. Now look what happens. Sampling distribution gets even wider. Okay, fewer clusters are being sampled, more variability. Okay, that variance is being driven by how many clusters are being sampled. Okay? It's like our sample size in terms of the clusters drawn is going down. So the standard errors are getting even larger. Okay, now we're up to 8.5 roughly in terms of that distribution. Okay? This widening of the sampling distribution, the increase in the standard error due to these cluster sampling designs, that's what we call the design effect. That's the effect of the probability sampling design on the variance of our estimates, not the bias, the variance. When we talk about the design effect, we're talking about the effect of the probability sampling design on the variability of our estimates. And this simulation is showing you how cluster sampling will spread out the variability of those estimates, or spread out the estimates themselves, I should say. Okay, so that's a sample size 500. Oh, George, you have a question? Yep.
So you're actually better off to use less clusters.
Well, this is the trade-off, right? So if you look at that middle option, right? We say, suppose your clusters are towns, let's say. With that middle option where you say you're going to sample 10 elements per cluster, you need to visit 50 towns. It's going to cost more, right? The third option, you're only visiting 10 towns, okay? Gas, travel expenses, hiring interviewers to work in those towns, it's going to cost a lot more, right? So you're getting less variability here in your estimate than you are in this approach, but at a much higher expense. That's the cost variance trade-off that sample designers need to think about carefully. So those of you in the sampling program, you're gonna spend a lot of time talking about that. Different sample design options with cost always under consideration. Is the reduction in variance that you're seeing here by visiting 50 clusters sufficient enough to justify the cost of doing that? That's the idea. Yep. So when you say what's better, that's a great question. We want the best possible estimates that are most efficient, lowest possible standard errors, but we also need to hit our sample size targets, right? That's the trade-off. So we're going to keep talking about that as well. This class is on analysis. So what we want to make sure we're doing in this class is that if this was the design actually used, okay, if that was the design used, I want to make sure that this is the standard error that I'm computing. I don't want to pretend that I had a simple random sample and severely understate my standard error, right? That's what this class is about. Making sure that we're accounting for the design features appropriately when we do the analysis. Okay. Now, as we go down the rows, look what happens. Okay. The bigger the sample size, the more precise our estimates. A bigger simple random sample, that sampling distribution of estimates shrinks. It's great. We can draw a sample size 5,000, we'll get a more precise estimate. It's going to cost money, right? Do we have the budget to go up to 5,000 as opposed to 500? Okay. If we do, that's fine. Standard error is going to go down. Still unbiased. Okay. Now, again, look across the columns. As we shift to cluster sampling to hit that target sample size, same thing. Okay, the sampling distribution is going to spread out even with a bigger sample size. So look at the comparison of this one versus this one. Okay. The takeaway message there is that a sample of 5,000 that's heavily clustered, 10 clusters, 50 observations per cluster, is giving you almost the same standard error as a simple random sample of size 500. That's the notion of an effective sample size. What's the size of a simple random sample? It's going to give you the same level of precision as your actual complex sample. So going back to power analysis, like we said on the homework and design effects, looking at this sample, you say, wow, I have 5,000 observations, but it's heavily clustered. If you're working with a calculation that requires the size of a simple random sample under IID assumptions, we need to use this quantity for those calculations. That's the size, the effective sample size that we're looking for in that case. We're going to come back to that idea, okay? But that's how we account for the design effect. We do these kinds of analyses. Cluster sampling really spreads out these distributions. Okay, so questions about the simulation idea here. The idea of unbiased estimates or sampling distributions or the spread of the distributions. Any questions here on the slide? This is just really important for the design-based thinking. This is the theory that we're using in the background. Okay, so Kish was the first to really lay out this notion of a design effect. And the design effect is simply written as the variability of a given estimate under complex sampling features divided by the variability of that same estimate under a simple random sample of the same size. Okay? So whatever the complexity is, stratification, cluster sampling, use of weights and estimation, maybe all three of those things, we calculate the variance of our estimate under those features, and we compare it in this ratio fashion to the variance of that exact same estimate as if simple random sampling had been used of the same size. And then this gives us a way to quantify the increase in the variance of an estimate due to the sampling features. At the same time, it lets us capture if the complex sample design features are decreasing the variance of the estimate. So it's entirely possible that we can come up with a really nice sampling plan that gives us a more efficient estimate than simple random sample of the same size. We're going to talk about that with stratification. Okay? So that too is also possible. But the design effect lets us quantify this inflation and variance using simple random sampling as a benchmark. Okay, so simple random sampling is seldom done in practice, but it's considered a benchmark to which more complex designs are compared. Okay, because it allows for easy computations and so forth. We want to see what's happening to the variance of our estimates under complex sampling. This also motivates really the point of the whole class. Again, these kinds of design effects, we're not typically going to compute them and report them in secondary analyses. But if that design effect is large, it gives you a sense of the implications of making an error that fails to account for the complex sample design features. If this design effect, for example, is 4, meaning that the variance of our estimate under the appropriate sample design features is 4 times as large as a simple random sample of the same size. If we ignore those design features in our analysis, we are understating our variance by a factor of 4 and our standard errors by a factor of 2 accordingly. Okay? So this gives you an idea of how much we're off in terms of our standard errors if we ignore our design features in practice. That's really what's important for the sake of this class. Okay? Now, where these design effects come from, roughly speaking, they can be defined using this function that you see here. They're 1, so that ratio kind of as a baseline is equal to 1, plus either gains, that's the G, or losses, that's the L, in precision due to these design features. Okay? So some function, people have tried to work out what that function looks like over the years, and there have been various attempts. But some function of stratification, cluster sampling, and the use of weights and estimation. Okay? Stratification will give you gains in precision. Okay? So the G strat refers to the relative gain in precision from stratified sampling compared to simple random sampling. So one of the things you'll hear a lot about in methods of survey sampling, when in doubt, stratify. Stratification always helps you in terms of the efficiency of your estimates. And we'll talk about effective ways to stratify. Okay? But the G means that you'll have design effects less than 1. If you have a stratified sample relative to a simple random sample, you'll tend to get design effects that are less than 1. So that's always a good idea. On the other hand, if you choose to use cluster sampling, which is often necessary from a cost perspective, you're going to experience losses of precision. That's what we just looked at in the graph. The sampling distribution spreads out. The estimates become more variable. You have less precision. Those all mean the same thing. Okay? When you choose to select a cluster sample, you experience that loss. That moves your design effect back in the direction of being above 1. Okay? The variance gets a little bit larger when you choose to use cluster sampling. The forgotten piece of design effects, hey, give me one sec, George. The forgotten piece is weighting. When you use weights in estimation, they give you that nice property where the sampling distribution is centered at your true population parameter. That's good for bias. But using survey weights in estimation also has implications for variance. Using survey weights in estimation will inflate the variance of your estimates. The more variable that those weights are, the higher that standard error is going to go up. So there's also a competing loss in precision if you choose to use weights in estimation. That's why we want to make sure that those weights are making a significant change in our estimates. They're reducing bias so that any additional increases in variance that we occur are offset by the fact that we're computing a more unbiased estimate. We're going to keep coming back to that point as well. Do we need to use the weights in estimation? Comparing weighted and unweighted estimates, do they seem notably different from each other? We'll keep coming back to that point. Okay, so what you see here, this general function for that design effect ratio, it amounts to a tug of war essentially. Stratification is pulling your standard errors down. Cluster sampling and weighting are pulling your standard errors up. Who wins in the end? That's the empirical question, right? When you account for all these design features, which you should be doing, what's really winning in the end? Usually, design effects empirically are going to be greater than 1. That's okay. That's the feature of the sample design that was used. It's just important that we account for it. If we just ignore that entirely, we're doing ourselves a disservice. Okay?
Once we would just wait for samples, by samples, this is actually giving more precision. And even, for example, if you're oversampling a subgroup.
Not precision, bias. That's where we want to keep this separate, bias and variance. The overall quality of an estimate is a combination of bias and variance. When we talk about precision, we're talking about the variance, right? So using weights, especially in the case of oversampling, that can be very important for making sure that we're getting unbiased estimates, but we also have to worry about the variance, precision. So that's, again, what's often forgotten is that just because I'm using weights in estimation, everything's not glorious. An estimate is not just defined by its bias. It's defined by its bias and its variance. That's the mean squared error. Okay, so that's the overall quality of an estimate. We need to keep both pieces in mind. And that's why this is so important. Yep. Okay, so it's about 10:05. Why don't we take about a 5-minute break, and then I'm going to jump into a little bit more detail about stratification, cluster sampling, and weighting, and why they have an impact on the variance of our estimates. And then we'll get into our discussion of weighting at the end of the lecture here. Okay, so let's take about a 5-minute break, and I'll start back up at 10 after. All right, thanks.
We check.
Oh, okay.
Yes, this was what happened. Yeah,
What was your question?
Question like we are discussing with the mass, it is coming in my mind maybe in our slide we are discussing about. But when we are determining the sample from the households around like health service. So when we set the design effect, normally we assume that is the design effect will be for each domain. Yeah, normally. So what is the concept behind this that we are setting design effect?
That entirely depends on past experience with a given survey. So usually that assumption about a design effect, like for calculation of sample size and so forth, is driven by empirical findings from previous surveys. So you've calculated a ton of different estimates, you've averaged the design effects for all those different estimates, and roughly speaking, the average is around 2 or something like that. Then that's carried forward to the design of a future survey to say, if on average the design effects may be equal to 2, how much sample do we need? What can we do with the cluster sample design, things of that sort. So the notion of that design effect is generally based on an average of many prior estimates. What you don't want to do is just grab that out of thin air and say that, let's use 3. It should really be driven by actual design effects observed in prior iterations of the same survey. That's the ideal situation.
So it is ideal approach that what we have done in the previous year. So the design effect we were having from the variables. So it is ideal to use such design effects for the next survey.
As long as like under similar survey conditions, right? Similar kind of measures, similar basic design ideas. Under roughly the same essential survey conditions, it's reasonable to bring that design effect forward and use it for future planning.
So it is ideal, like you were talking about the design effect. So after computation, applying pairs, but we are getting the tables, like when we are driving tables regarding the standard errors, we are computing design effects, coefficient of variation, and confidence interval at the end of the survey, like reporting method. So for example, we have a variable for breastfeeding for mother, and it has design effect like 5 point something. So it is going like idea of good estimator we have computed, or like it's less reliable.
It goes back to the objective of the survey. If the survey is only interested in that variable, like breastfeeding, then you'd want to account for that design effect of 5. But if it's a multi-purpose survey where you're measuring breastfeeding and you're measuring a bunch of other health variables, right? That's where averaging makes a little bit more sense, because you want to say, what sample size do I need on average to give me the precision I'm looking for?
So right, like I'm giving example of the mix already. Yeah, we are computing 200, approximately 200 indicators. Yeah. So in that case, this like the design effect for this indicator is helpful in the future. Or
and it's like when you analyze micro data and you want to compute an estimate. One individual design effect is probably not as meaningful as the overall average and the variability of design.
But we are computing like for the all the women.
All the so you might have one average design effect for women, one average design effect for men. That informs the samples that you ultimately select. But yeah, in a multi-purpose survey, you're generally talking about like a mean or a median. Some people model design effects. So they say like as a function of sample size, what's the design effect going to be? There's different ways to do that, but it's always referring to aggregate design effects, not any one individual.
So it helps in the survey, like we are having the reliable estimates with the 5 design.
Well, you always want reliable estimates to be sure, but if you're using these design effects for future planning, right, you just want to take all of them into account, like the full distribution, not just focus on 1 or 2.
So to what extent we can have, like we would say that for example, we are having a design effect near to 8 or 9 for any variable. So would it be again the acceptable variable to?
I mean, there's no magic number, but if you're seeing a design effect of 8 or 9, something's off. Because that's a massive amount of variance inflation. It's either the variability of the weights, or there's super high intra-cluster correlations. Like, we'll talk about where the design effects come from, but if you're giving data users an average variance inflation of 8 or 9, it's not ideal.
So it might be appropriate for few variables, but not appropriate for the rest of the variables.
It totally depends on the objective of the study.
So many variables.
Yeah, it depends. It just depends on if data users are only working with these 5 variables, then look at the design effects for those 5 variables.
Then
It just depends on what users of the data are going to be doing.
Thank you. Thank you.
How long did it take to?
Okay, I think we're going to start back up here. Okay, so we were talking about design effects and kind of the sources of the different design effects. The three big drivers of design effects, as were just defined, are stratified sampling, cluster sampling, and weighting for different selection probabilities. Those are the three big drivers that have the biggest impact on that design effect ratio. And there are these other smaller pieces associated with sample designs that will affect the variance of the estimates, but not to the same extent that stratification, cluster sampling, and weighting will have. Okay, so that's our focus. I also want to bring up a point that came up during the break. Remember that the design effect is specific to an estimate. So if the design effect is not a property of a survey, the design effect is a property of an estimate. So if you're managing a survey that's providing data on 1,000 different variables, you're going to get 1,000 different design effects at least, if we're just talking about descriptive estimation, let alone regression modeling or anything else people might want to do with the data. A design effect is a characteristic of a single estimate. So if you're fitting a multivariable regression model with 10 predictors, you're going to get 10 design effects for each of those estimated coefficients. Remember that it's a property of an estimate, not a survey. So it's not correct to say this survey produces a design effect of 2. You have to say this survey produced a design effect of 2 for this estimate. If you're trying to characterize tendencies of a given survey, you might take an average or a median of all those different design effects for planning purposes. Okay. So remember, it's a property of an estimate, not a survey. Okay, so let's talk about these pieces. I talked about the tug of war idea. So this on slide 24 here, this graph shows the expected standard error of an estimated proportion that's equal to 0.5 under simple random samples of a particular size. So that black line is showing the standard error that you'd expect to see under a simple random sample of a particular size. So you see that after about 2,500 cases, you're not getting any gains in efficiency from a bigger sample for that particular proportion estimate. The arrows show you how those different design features pull on that standard error and shift that curve up or down for a sample of the same size. Okay? So weighting and cluster sampling, they're going to shift that standard error up in general. Stratification is going to pull that standard error down. And again, it's an empirical question of what in aggregate results from these complex sampling features. The key point for secondary analysts is that you're accounting for these features when you do the analysis, and that you're not ignoring any of these arrows entirely. Again, a very, very, very common mistake when people are first sitting down to analyze data from complex samples is they only account for the weights and estimation. That completely misses both of these pieces. And that's a critical error in terms of the way that variances are being estimated. Okay, so that's a crucial point here. So keep this tug of war in the back of your mind when you're thinking about design effects. Okay, what are these pieces? So one of the minor pieces of a design effect is this finite population correction, or FPC, okay, as it's abbreviated. This is a piece of the design effect that comes from sampling without replacement. Okay, this is entirely a characteristic of sampling plans that involve without replacement selection. The FPC is the proportion of the population that was not sampled. Okay, so what fraction of the population was not sampled? Generally, that fraction is 1 for huge populations. So this multiplicative FPC term usually gets ignored in practice with large national probability samples. Smaller scale samples, local areas, small populations, maybe the FPC gets a little bit larger, okay, but, or I should say smaller in this case, but typically it would get ignored in practice. Okay, so just to show you what it is, suppose you have a simple random sample. Okay, the sampling variance of the estimated mean of a variable y is written as you see here: 1 minus the fraction of the population that was sampled, or the sampling fraction. Little n is the sample size, capital N is the population size, times, here's our S squared again, I'm going to keep using that nickname, times the element variance for the variable y, not the sampling variance, the element variance. the variability of that single variable y divided by the sample size, okay? And so this 1 minus f term, where f is the sampling fraction, that's the finite population correction.
Okay,
So
this is where here is element population.
element variance, right? So it's you can come up with an estimate of that for the population. We just have a sample, right? So this is the estimate of the variability of the values on the variable, not the sampling distribution.
Yeah.
Yep. So that's what S squared is in this case. Okay. So 1 minus F, that is the FPC term. So if that sampling fraction is close to 0, the FPC is going to be very close to 1, and it doesn't make a difference compared to with replacement sampling. With replacement sampling, this variance would just be S squared divided by N. Okay, this term comes in because of without replacement sampling. And if that sampling fraction is tiny, we don't need to worry about it. Okay, this is the formula for stratified random sampling. We're not there quite yet. The point is that if we do simple random sampling within strata as a part of the design, FPC comes in the same way. It's still 1 minus F times S squared divided by N. We just have that additional WH squared term, and I'll show you where that comes from. Okay, so same idea, but if the sampling fraction within strata, F sub H is tiny, still reasonable to ignore these. Okay, software does give you the option of specifying the FPC if you think it's going to make a meaningful difference in terms of your variance estimates. So software does let you set it, but typically that sampling fraction is going to be pretty tiny relative to the size of the population. So that's why it's considered a relatively minor piece of the overall design effect. Okay, so moving forward in this class, we're typically going to ignore the FPC for the sake of variance estimation. Okay. Stratification, stratified sampling, one of the other big players. So for those of you in methods of survey sampling, you're going to spend a lot of time talking about stratification. Those of you who are not, this is just a quick overview of why it's important to think about stratification as part of the design for variance estimation. The basic procedure, you form different strata. These are divisions of your population. Okay? So using sampling frame information or auxiliary variables available for your full population, you divide everybody in your population up into these mutually exclusive groups. And you account for every single possible stratum in your population. So nothing's been omitted. Okay? And then you do independent sample selection within each of the different strata. You allocate some amount of your sample to each of the different strata. You might have completely different sample designs in each of the strata. Simple random sampling in one, cluster sampling in the other, it doesn't matter. Okay? You do independent selection in each of the different strata. That yields an estimate for each of the individual strata. So if you were interested in estimating a mean, you'd have this Y bar sub H for each of the different strata. And then we can compute an overall estimate by looking at the weighted average across the strata. Okay? So here we're just summing those means for each of the specific strata multiplied by this WH term. That WH is the fraction of the population coming from that stratum. You see, it's the size of the population, stratum H, capital N sub H, divided by capital N. Okay, so it's like a weighted average grade in a course, basically. Bigger strata, bigger contribution to that overall mean. Okay? So if we're going to write down the sampling variance of that particular mean estimate that we see here, you see that we have a constant WH times a random variable, the mean within stratum H, right? From one sample to another, that mean within stratum H is going to vary. It depends on who we randomly sample within each of the strata. Okay? That WH is a constant. So remember, if we take the variance of a constant, I'll call it C, times a random variable, which is going to vary across hypothetical repeated samples, what does that yield? It yields C squared times the variance of that random variable. Okay? So that's what gives rise to the expression that you see there. If those strata are mutually exclusive and independent, the variance of the sum is the sum of the variances. Within each stratum, the variance is the constant squared times the variance of that random estimate, which varies from sample to sample. Okay? That gives rise to the formula you saw on the previous page, if we were doing simple random sampling within each of the strata. Okay? And we would estimate that in practice with the data that we actually collect from a given sample. The key thing that I want you to observe about stratified sampling The overall variance of that estimate is entirely defined by within stratum variance. The variability between the strata in terms of our mean of interest, don't even see it here. Why? Because it's fixed by design. Every single hypothetical sample is always going to feature the same sample selection from the exact same strata. There's no variability. If we were to go out and draw thousands of hypothetical samples under Neyman's framework, and we use the stratified sample design, every single one of them is going to have the exact same allocation to the exact same strata. No variability. Okay? That's why the between stratum variance doesn't even enter here. The entire sampling variance is governed by within stratum variance. Okay? When in doubt, stratify. Okay? Because relative to simple random sampling includes the between element or the between stratum variance. That S squared term, that's the sum of the between and the within stratum variance in terms of our variable of interest. So stratified sampling is going to reduce our sampling variance because we're removing the between stratum variance from the equation entirely by design. When in doubt, stratify. You're going to get those gains relative to simple random sampling. We'll see that empirically here in a second. But that's why stratification is so important. It removes the variability between strata from the sampling from the equation entirely. Okay? So it's a fundamental feature of sample designs, and that's why it's so important to account for in variance estimation. So again, if an analyst was just using the weights in the analysis, when stratum codes and cluster codes were available, they are doing themselves a disservice because they're not getting the gains from stratification that we see here in the way that the variance is estimated, right? That's what's absolutely crucial for the stratified sampling idea. Okay, erase this here real quick. Okay, so let's just see an example of what we mean by this kind of gain and efficiency. Suppose that we have a population where we have two strata. Okay, so very simple case. We have an urban stratum and we have a rural stratum. We divided our entire population into these two groups. It includes everybody, the population. We know the size of the population in each stratum. So 80% of the population comes from the rural stratum. Okay? We know the variance of our variable of interest within each of the strata. This is the capital S squared. So this is the known population element variance for some variable of interest. Okay? We also know the population mean for the variable of interest within each of the two strata. So if you had these data in hand, there's no point in doing a survey. You already know everything, right? The purpose of this illustration is to illustrate the gains in efficiency from stratified sampling, given this known information that we would usually be estimating in practice. Okay, so suppose we knew this for the two strata. Here's the variance of a stratified mean given that information for a sample design that was proportionate in nature of size 1200. This is called proportionate allocation, right? So we had enough money to select a sample of size 1200. We allocated that sample proportionately. 20% came from the urban stratum, 80% came from the rural stratum. Okay, that's the sample design. Every hypothetical sample in Neyman's framework, same allocation. No variability, same strata every time. Okay? The variance of that estimated mean under this sample design, same formula you saw on the previous page. The sum over all the strata of the FPCs times that squared fractional weight, the element variance divided by the sample size. Okay? Now, you will see how I'm spreading this out here. I'm removing the FPCs. That's the approximate equal sign. I know the sizes of the population in each stratum. These sampling fractions are tiny. That's why you see the approximate equal sign. I'm just getting the FPCs out of the equation. Okay? Now, I'm just plugging in the known population quantities. Again, we would not have these in practice. This is theoretical. Okay? I'm just plugging in the known population quantities. Okay? Fraction of the population in each stratum, element variance within each stratum, sample size allocated to each stratum for this design. Okay? All that combines to give me a theoretical variance, capital V. This is if I knew it for everybody in the population. Theoretical variance of 1333. Okay, so you look at that, and you say, okay, that mean would have that sampling variability under this design, 1,333. And you say, so what? Okay, that's great. That's one design. Okay. Thinking about design effects, we ask the question, what if we had just selected a simple random sample of size 1,200? Okay. Okay. Same sample size, same cost potentially, depends on the stratification. What happens to our variance? Theoretical variance of the mean under simple random sampling, same formula I showed you on the previous page, FPC times element variance divided by sample size. But that S squared combines between and within variance, right? So our simple random sample variance is going to go up relative to stratified sampling. Again, I'm ignoring the FPC. You see the calculation, 1,500. Theoretical variance. Before, it was 1,333. If we calculate that design effect using Kish's ratio, the variability of that estimate under complex sampling, under the stratified design, was 1,333. The variance of that estimate, same sample size, 1,200, under the simple random sample design, was 1,500. My design effect ratio is 0.89. I am getting gains in the efficiency of the estimate from the decision to stratify. Why? Because I'm removing the between stratum variance from the calculation by design. It doesn't contribute to the sampling variability at all. Okay, so I get an 11% gain in my efficiency. Okay, increase in precision from that decision to do a stratified sampling. And again, we would typically estimate this design effect ratio based on our sample data. We're not going to have access to the population data. Otherwise, we wouldn't be doing a survey, right? This is just to show the theoretical calculation here. Okay, so design effects can be less than 1 if in aggregate, the design features shrink the variance in this way. But this is again, where when you're sitting down to analyze data, you think you just have to use the weights or you'll be good without this, with ignoring the other design features, you miss this game. You are harming yourself in that the standard errors are larger than they should be if you had accounted for the stratified sampling. That's why it's so important to fully account for all these design features when we do the analysis and not just assume that the weights are doing all the work. Okay. Now, talked about that idea of the effective sample size that has the problem on the homework. So the effective sample size is closely related to the design effect. The effective sample size tells you what would be the size of a simple random sample that would be necessary to achieve the same precision or the same variance as the given sample design, as the given complex sample design. Very simple calculation. Just take the actual size of your complex sample and divide it by the design effect. That gives you the size of a simple random sample that will give you the same variance as your actual complex sample. So, say again?
From the strata.
In this case, I'm just in general, the way this is calculated, the design effect could account for anything that we've talked about. Here, we're just talking about stratification. Okay. So here, the design effect was 0.89 based on our calculation, right? So we divide our actual sample size of the complex sample, 1,200, by 0.89. That gives us 1,348. So if we wanted to draw a simple random sample that would give us the same efficiency as the complex sample, we would have to go out and select a simple random sample of 1,348. Would we do that? Not a chance. It's going to cost more money, right? That's the idea of the effective sample size. Now, as I mentioned, in aggregate, design effects are going to tend to be larger than that when we account for all these design features. So typically, the effective sample size is going to go down relative to your actual sample size. It just depends on the nature of the design effect. Okay, so we're going to keep coming back to this idea, but if you're writing a grant proposal or you're writing a study design or something like that, and you need to do power calculations assume IID data. They assume simple random sample data. So when you do those calculations, you have to input the effective sample size, not the nominal sample size that you think you have. So if you had a design effect of 4 or 5, or like Isaac was telling me, 9, right? You might think you have 10,000, you really don't. Okay, effective observations, when you account for the increases in variance, may be far fewer than what you actually have in your data set. That's what the power analysis calculations are looking for. Okay? And remember, hint, hint for the homework, the design effect is a ratio of variances, right? The variance is the squared standard error. So you could think about design effects in terms of standard errors or variances. But in the effective sample size calculation, you're going to use the ratio of variances. Okay? You're dividing the sample size by the design effect the way that Kish described it. Okay? Everybody clear on this point?
Yes. But what about if I have a simple random sampling, and then I want to know the actual size of the sample that gives me the same precision in strata.
You would just flip, you can flip this around, right? If you have the effective sample size, you could solve this for the actual size of the sample you need under your complex design simply by multiplying the effective sample size by the design effect. Just flip this around, right? Just simple algebra.
Yeah.
So this means that in a complex design, we have a 1,200 sample size, and if it is simple random sample, we go up to 1,348.
We would need 1,348 to achieve the same standard error, right? Which is useless, right? We would never do that. It's expensive, right? So we'd never do that. We would choose the stratified sampling 100% of the time.
Yeah, another bit.
Okay.
If you go back slide, this one, another one. Another one.
Oh, so what you got? Tell me which one.
Like my question was like, why the variance, for example, sometimes is greater than the sample size?
We're still just talking about stratified sampling. So that's, we got to remember, Kerry, we haven't even talked about cluster sampling or weighting yet. This is just assuming you have a stratified simple random sample. That's it. So we're starting with a very simple example of one type of design. We still have to talk about all the other aspects.
Even within this strata,
Mhm.
like the variance can be greater than the sample size.
So I'm not sure what you mean. So
The other one, I'm sure. Yes, like here.
that's the element variance. Remember, this is not the sampling variance. S squared here is the variability of the variable of interest, not the sampling variance. We have to keep those two concepts separate. Yeah, this is the variability. If we were to plot all the values on this variable of interest for the entire population, that's what S squared would be, the variability. This is the variability of the elements. This is not the variability of the sample estimates. Those are two different concepts.
What is the difference between this, the element and the population one?
This is the population element variance.
Yes.
We could estimate this based on the sample. This is assuming that we have data on every single person in the population.
Oh, yeah.
These are two full population data sets. Typically, we would have a sample. We would have to estimate that capital S squared. I'm just giving it to you. So almost always, that's going to be larger than the sample, depending on the variable you're looking at. Yep. Okay. So slide 32 just talks about what I've been talking about all along about how we get rid of the between stratum variance from the sampling variance calculation with stratified sampling. Okay. So the gain that you achieve in precision, if we look at the variability under simple random sampling, and then the variability under stratified sampling with this specific proportionate allocation that we looked at, that difference is going to be defined almost entirely by the between stratum variance. Okay? That's what we're just ignoring entirely when we decide to stratify. And so what you hear about when you're forming strata is form strata that are as different as possible in terms of the variable of interest, okay? Because the bigger that between stratum variance, the bigger the gains in efficiency that you see here. We're removing more from the simple random sample variance, the more variability that there is between the strata in terms of what we're trying to measure. So when you're defining those strata by design, you want to make sure that they're as unique as possible in terms of what you're trying to measure, that's what's going to achieve the highest gains in terms of your design effect. Okay? So that's the job of the sample designer. Okay, so that's stratification. Another key thing that we have to keep distinct in our minds moving forward is the distinction between strata and clusters. They are not interchangeable. They are very different concepts. Strata are all possible divisions of the population where we allocate some of our sample to be selected from each of the different strata. All the strata are represented in our complex sample design. We have some sample allocated to all the different strata. They are fixed by design. Strata are a fixed feature of the sample design, no sampling variability. We don't randomly sample strata. Okay? Not a feature of any sample design. Clusters, on the other hand, are units of elements that we're interested in that are actually randomly selected. So we might randomly sample clusters of elements within strata. We might just select a cluster sample of elements overall without any kind of stratification. But clusters are randomly sampled. This is where random sample variance comes into play when we randomly select clusters. These are naturally occurring groups of elements that we choose to sample for one reason or another. Okay? And we often do cluster sampling because we can't afford to visit little n randomly sampled units that come from some large, widely dispersed geographic area. It just costs too much money to draw a simple random sample. So instead, we randomly sample clusters and then we send our staff to those particular clusters to do the data collection, like we talked about with N. Haynes on Monday. Okay? So primarily, cluster sampling is done to reduce the cost of data collection. So you could sample schools and sample children within the schools. You could sample blocks or neighborhoods and then sample households within those blocks. Those are all examples of cluster samples, where we're drawing on naturally occurring groupings of elements to get to the sample that we're ultimately trying to measure. Okay? All to save money. So clusters randomly sampled within strata. Okay? Strata fixed by design. No sampling variability whatsoever. Okay? Help to increase our precision. Okay? Cluster sampling can also be useful when the sampling frame lists clusters and not elements. Okay? So we may not even have a list of all the elements in our population. We may only have a list of neighborhoods or schools or clinics or enumeration areas or whatever the case may be. We have to sample from that list first before we can actually sample our elements within each of those areas. So sometimes it's a necessity to draw cluster sampling. It's not even a cost-saving issue. It's all we have to work with. Okay? So that's often a reason cluster samples are selected as well. So you might have a sampling frame of blocks or neighborhoods. You could draw a random sample of blocks and then list the households within those sampled neighborhoods and select the households that you want to work with. Okay? So primary reasons to do cluster sampling. But let's think about, we saw that simulation study earlier where we looked at the effects of cluster sampling on the sampling distribution. Let's look at some actual data here and see what happens in terms of that design effect. So let's assume that you have a town with 500 blocks in total within that town, something like the city of Detroit or something, with a very large number of blocks or neighborhoods. So let's suppose there's a total of 500 blocks, and each of the blocks in that town has exactly 24 kids in that block. Okay, so a toy example, but let's just see, again, for the sake of illustration, see what happens here. So by design, you choose to select a simple random sample of 10 blocks from that list of 500, and then you examine the immunization history of all the children in those 10 selected blocks. So there's no subsampling. We just measure everybody within each of the clusters. Okay? So the ultimate sample consists of little n equals 240 children, right? 10 times 24. That's our sample design. Okay? In this context, we would refer to the capital A clusters within the town as primary sampling units, or PSUs. Those are those clusters that are sampled at the first stage of selection. So no stratification. This is just a cluster sample. We can think of everybody as coming from one stratum. Okay, no division of the population. So for each of the 10 PSUs that are included in the sample, you can exactly compute the proportion of children that were immunized based on the data collected. So we assume there's no non-response either. Okay. So suppose these are the data that we actually collect. Okay, so the variable of interest Y is a binary variable. Were you immunized or not, the kid in that household. And then the proportion is just the sum of those binary values divided by the number of kids in the cluster, or just B. That's the proportion for the cluster. So here's the actual cluster specific estimates. That's what I want you to look at. That is the data for the sake of variance estimation, not the micro data. This is another key change in mindset relative to your other applied statistics courses. With stratified cluster samples, the cluster quantities are the data that we use for variance estimation, not the individual microdata. Okay? So we don't have degrees of freedom close to 240. We have degrees of freedom closer to 10 in this case. Okay? It's the cluster quantities that drive our variance estimates in these kinds of clustered probability samples. Very essential point here. Okay? So these cluster specific proportions, those are the data that we're working with. And what you see is that there's a ton of between cluster variability. Some clusters, less than half of the kids are immunized. Other clusters, almost every kid is immunized. Okay? There's a lot of variability between the clusters. What that equates to is a lot of correlation of people within the same cluster. Depending on what cluster I'm talking to, kids are going to tend to be not immunized, or they're going to tend to be immunized. That's an intra-cluster correlation of the variable that we're trying to measure. So the higher that ICC, and accordingly, the higher the between cluster variance, the more the sampling distribution is going to spread. That's the idea. And that's where you always hear that common guidance. If you're working with cluster data, there's going to be a correlation there that's going to make your standard errors go up. That's why. Okay? It's the idea of an ICC here. So again, thinking about the design effect. Suppose you have a simple random sample of 240 children, same sample size. Design effect is always talking about a simple random sample of the same size. And you produce an estimate of the proportion immunized, just like we saw on the previous slide, overall of 0.667. Okay, so 2/3 of kids are immunized. That's our point estimate. Okay? Under simple random sampling, here's the formula for the variance of a proportion. FPC, that P times Q is P times 1 minus P, or P times 1 minus the proportion. That's our S squared for binary data. Some of you might remember that. Okay, so that's S squared basically in the numerator. And for proportions, we actually divide by N minus 1. That gives us an unbiased estimate. Okay. That calculation, the variance of the proportion, looks pretty tiny, right? But it's all about relativity with sample designs. We want to see what that looks like relative to the cluster sample, thinking about design effects. So for the cluster sample, we calculate the variability based on the variability in those proportions for the specific clusters, not based on the microdata, but based on the variability in those proportions. That variance is 0.0027. We're going to see what those formulas look like. But the inputs to that variance calculation are the cluster specific proportions, not the microdata. That's the difference here. When we look at that variance, it's 3 times the size of the SRS variance. That's the unbiased estimate of the variance of the proportion under the cluster sample. Okay? So the estimated variance of the same proportion under the same sample size is 3 times larger in the case of the cluster sample. Okay? Here's the design effect calculation. We simply take the variance estimated under the complex sample, divide by the variance under a simple random sample of the same size, 3.029. Stratification, G. Cluster sampling, L. This is what you tend to see in practice. Okay? And the question is for the design effect is what happens in aggregate between those two things. Okay? So effective sample size calculation, the actual size of our complex cluster sample is 240. Divide it by the estimated design effect for this particular proportion, 3.029. A simple random sample of size 79 would give us the same precision as our cluster sample. So you look at this and you say, well, what the hell? Why are we dealing with cluster sampling? Let's just go draw a simple random sample of size 79. Money. That's the cost variance trade-off. Sure, we'd love to go draw a simple random sample of size 79. But if it's going to cost 10 times as much, I'm not going to do it, right? So that's the idea. We might choose the cluster sample to save money, allowing for the loss in efficiency due to the cluster sampling. As secondary analysts, it's just important that we take that design effect of 3 into account. And we don't pretend that we had a simple random sample of size 240. That's the idea of the effective sample size. Okay, now Kish also showed that you can rewrite the design effect using this expression here in the case of cluster sampling. And this was very informative because it shows that you can define the design effect in cluster samples as a function of 2 parameters of the sample design, okay? So you can write that design effect as 1 plus this quantity B minus 1. B is how much sample is selected from each cluster on average. So in the case of this toy example, we had 24 kids measured in each cluster, so that B would be 24. Okay? Now, that's one of the parameters. The second parameter, that B minus 1, is multiplied by rho. Rho is this idea of the intra-class or intra-cluster correlation. The correlation of any pair of observations coming from the same cluster. Okay? Now, how can we calculate that rho? Again, basic algebra. You can flip around this formula here that Kish derived and calculate what he called the synthetic estimate of rho based on the design effect calculation. So we just need the estimated design effect, and we need the size of the sample from each of the clusters, 24 in this case. So that calculation, if we just carry it out here, the estimate of rho is 0.088. What that means is that any pair of children coming from the same cluster, the correlation of their binary variables is going to be about 0.09. Okay? And that's on the high end of what you'll typically see in practice. That interclass correlation usually going to be between 0.01 and 0.05. It's not nothing, but it's not going to tend to be huge. Okay, longitudinal data, if you're looking at a person as a cluster, that correlation is going to be a lot bigger. Okay, but for cross-sectional cluster samples, probably between 0.01 and 0.1. You're going to tend to see that. It still does play a role in the design effect, but not as big of a role as B. And that's a choice of your sample design. How many people you sample from each of the different clusters. Again, keeping cost in mind. So this was a very informative derivation. Again, thinking about designing future samples and thinking about what's driving the variance inflation, okay, for a given estimate in the design effect. So a different way of writing the design effect here. So again, that intra-cluster correlation, not something we control. Okay, with sample design, we're always worried about control. Like, what do we have control over from a scientific perspective? This rho is just a property of whatever naturally occurring clusters you want to work with, whether they're hospitals or neighborhood blocks or whatever. You don't have a choice. Okay, rho depends on the clusters that you define for the cluster sampling. For human populations, it's always going to be positive. There's going to tend to be a positive correlation for people coming from the same cluster, and that could be due to the environment. People are exposed to the same climate or hazardous waste spill or some kind of infectious disease. It could be due to self-selection. Wealthy neighborhoods tend to contain wealthy people. Poor neighborhoods tend to contain poor people. Okay? Interactions, people sharing the same political attitudes about health. People living next to each other, always talking about the same thing. Okay? Shared attitudes. The magnitude is going to depend on what variable you're studying. So different variables are going to have different rows. The nature of the clusters you define, are they households? Are they city blocks? Are they schools? The sizes of the clusters, okay? All of that's going to drive rho, but you have no control over it. You can estimate it and then use it in sample size decisions, but we have no control over it. Analytically, again, we just have to make sure that whatever design effect that's arising due to cluster sampling, we're accounting for it when we do our analysis. That's the key thing. The rho is really one of the 2 main drivers here. Now, in that example, we took all kids within each cluster. More often, there's going to be some form of multi-stage sampling, like we talked about in Haynes. Okay? So suppose your sample design called for a sample of little a blocks, but then little b children from each block. Now you have a decision to make about little a and little b. Okay, what should those be to produce a sample of size 240? We have all these possible choices, right? 80 blocks, 3 kids per block. 20 blocks, 12 per block, et cetera, et cetera. Okay. All of them are what you're going to learn about as being equal probability of selection mechanism designs, EPSM. It's another term that Kish like to play with, okay? Meaning the overall probability of being included in the sample is always going to be the same, no matter your choices of A and B. Okay, assuming you're doing simple random sampling at each of those stages. So you have choices that are always going to give kids the same probability of being selected, 1 out of 15. You just have to choose what you want for A and B, and that has different implications. Fortunately, Kish showed that the design effect for that 2-stage sample design, same calculation. Now we're just using little b, the amount to subsample from each of the clusters, as opposed to taking everything. So it's whatever the sample size per cluster is, that's the b that gets used in that design effect calculation.
So the cluster sample is always stage.
Yeah, this is 2-stage sample.
Always, the cluster sample is always.
Oh, no. We like remember N. Haynes from Monday. That was a 4-stage cluster sample, right?
Multi-stage, I mean.
Multi-stage in general, yeah. This is just a simple illustration of 2-stage. For the toy example with the kids that I was talking about.
The children's holiday secondary.
Yeah, so in this case, we could call it children the 2nd-stage units, or the SSUs. That's ultimately who we're collecting data from, so that's a bit of overkill, but that's the way to think about it. So here's what the typical sample designer would look at in making those choices, right? All of these choices for little a and little b give us the same sample size, okay? But they result in different design effects and different effective sample sizes by definition, okay? Notice that we're using that synthetic estimate of rho portably across these different design choices. We're assuming that's a naturally occurring property of these clusters that we have no control over. So we're going to use that same value of rho in these design effect calculations. But the different implications for the calculation of B does change the design effect, even for the same value of rho. And that's what we see here. So, right, if you look at this table and you were the one being paid to design this sample, what do you choose? You choose the 80 clusters to visit, only taking 3 kids per cluster because it gives you the biggest effective sample size? Or do you choose 10 clusters to visit with 24 kids per cluster because it saves you the most money? This is why sampling statisticians get paid the big bucks. That's why you guys are here, right? These are the decisions that you're going to learn how to make. But right, the ideal thing would be to make a trade-off. Again, cost versus variance, okay? Probably we're going to end up somewhere in the middle in terms of the overall design choice. Maybe 30 clusters, 8 kids to measure per cluster, a moderate effective sample size. But these are the discussions that have to go on, okay? Again, from a design perspective, this class is about analysis. So the main message here, all of these design effects are between 1 and 4. That means that a failure to account for the cluster sampling when you analyze these data would lead to severely understated variances. And that's what we want to avoid. Okay? We expect cluster sampling to inflate our variance. We just need to account for that when we analyze the data. Okay, everybody with me? Okay, Georgia.
So if you don't account the last option, it's the one that is closest to 1. So that one, in terms of the extended errors, that will give you the, if you fail to account for those issues, that's a big complex design. It will give you the one that it's not going to do much.
Not a huge loss, right? But you're going to be spending a boatload of money visiting 80 different blocks, right? That's the trade-off. Yeah. Always got to keep costs in mind. That's right. Okay, good. So let's turn with the remaining time. I want to talk about weighting briefly, and then we'll. Question?
Yeah, I'm concerned with the design effect. For reliable estimate, is there a range within which the design effect should fall?
No, yeah, there's no magic number of the design effect where you would look at that number and say, this is a reliable estimate. The design effect is just a byproduct of the sample design that needs to be accounted for in analysis. So you want to try to keep the design effects reasonable. Like we were just talking to Isaac, like, you know, if you're seeing something that's like 8, 9, 10, probably want to rethink what decisions you're making, because you're automatically inflating the variances of estimates being computed by your data users by a factor of 10. And that's going to make it very hard for them to detect certain relationships or have reasonable sized confidence intervals. You got to look back and see what's driving that. So something 1, 2, maybe 3 or 4, that's typically what you'll see in public use data sets. Again, because you have to keep the data users in mind. Like you're going to be, if you give them weights and cluster sample codes and stratum codes that give them on average design effects of 8, 9, or 10, you're automatically handicapping them before they do any analysis, right? And sure, that might reflect the design, but you got to go back to that design and say, well, what about that design was really causing this? Is it that the weights are too variable? Is it that we chose a design that had, you know, too many samples selected per cluster? Like, what can we change in that case? So it's a challenging problem. But again, for the sake of secondary analysis, we just need to be aware that there is a design effect. And when we do the analysis, that we're accounting for.
George, I have another question. The design effect of 2, I don't know, that value of 2, where does that value originate from? If you don't know, if you
Magic.
Any prior, right?
Yeah.
Is it just
No,
something that-
never. This is what I was talking to Isaac about during the break. Never just make up a design, ever.
Because in some
It should-
textbooks, in some textbooks, they say if you don't know.
It's
don't
garbage.
have it, then it's done.
It's garbage. Don't make up a value. Even if you have a partially related study of similar measures conducted by some other agency, calculate estimates of design effects from that other survey, even if it's only tangentially related. You do not want to invent design effects out of thin air. So I would want, if I was reading that, I'd want to see a citation, because you can't just invent a quantity this important out of thin air. It has to be driven by other similar data collections or something like that. Never should just be made up. In the same way that you should never make up what stratum variable, what cluster variable you're going to use in analysis. Never. It should always be evidence-based. So yeah, I can't give you a citation for a magic number of 2.
Because from what I read, I think generally, I don't know, that's what for me, I always wanted to know. When you are saying that a complex sample design generally yield twice as much. As what it is.
Never. Never.
I don't know, so I've always wondered.
No, there's no origin of it. It's hearsay. Like you say, a complex sample design like this yielded an average design effect of 2 based on this table of 100 design effects, then I'll listen to you. If somebody just says this complex sample design gives you 2, show me the evidence. Always. Yep. Jupiter, you had a question then.
Yeah. So partly, I think maybe it has been answered from as you're responding to George, because you showed the formula for the effective sample size, and so we have design effects that are said there, and but then the design effect is the ratio of variances,
right?
And in most cases, we don't know them. So
no, you have to estimate them based on a given sample. So that's what that's what I'm saying. If you're trying to motivate a future study, find a somewhat related survey that's already been conducted. Go into that survey, find some similar measures that you're trying to collect, compute a bunch of descriptive estimates for those measures, save the design effects, calculate the average or the median design effect that you see there. Now you have some evidence to go on, right? You're estimating the nature of those design effects from another related study. Now you have evidence. Now you can say, I believe that a better estimate of that design effect, given a study with similar design properties, is going to be 3 or 1.5 or whatever it is. But just drawing a number out of thin air and saying it's going to be 2 no matter what, it's nonsense. Make it based on evidence, and just you can estimate these design effects from other studies that are available online or other places. So, question?
Node population get you more chance to do good stratas, and then you can sample clusters inside the stratas.
Right.
And in your experience, how time it's a problem in this equation, because our sample think about the gain you have combining the different designs, but in time. Because if you, for example, if you take more clusters inside the stratus, you get better stationaries.
If you can afford it, yeah.
Okay, but how time is entering this in this? Because you have time to do the research.
Yeah, the cost, I mean, you know, time is money, as you say.
Yeah.
So you have a certain schedule under which you want to complete the data collection, but you also have to hit a certain budget. So if you select more clusters within a stratum, certainly that's going to take more time, more staff. That's always a consideration as well. So it entirely depends on a project's budget and timeline, whether a particular design like that is going to fly in the context of that budget and that timeline. It just entirely depends on the project and how many resources are available. Once you have a fixed number of resources and you're aware of those constraints, then you can evaluate these different possibilities for how many clusters to sample. But time should always be accounted for as well. Okay, we're a little bit after 11, so I think we'll actually stop here and come back to waiting on Friday. You can feel free to read ahead in these slides. I'd much rather answer questions like this, to be honest. So these questions are all great. Feel free to read ahead a little bit in the slides, but at the beginning of the lab on Friday, we're going to start by going over weights again, and then we'll talk about the design variables that get included in these survey data sets and where they come from. So, you know, we'll talk about where weights come from, but we'll also talk about what gives rise to the stratum codes and cluster codes that you see in these data sets and some of the assumptions that we make before we dive into some of the data sets with the computer lab notes on Friday. So on Friday, the first computer lab notes have been posted, so you can take a look at those as well. I'm going to be walking through running those analyses, executing those codes in Stata and RStudio. So again, starting on Friday, you can follow along with this if you would like, but we'll finish up with our discussion of weighting and then the origins of these design codes before we jump into those lab notes on Friday. Okay, so I think that'll be our plan. And definitely reach out if you have any questions about what we talked about for the first homework assignment or about the final project in teams or data sets that you're thinking about. Reach out if you'd like to discuss that further. Okay. Any questions or any additional questions though about our discussion of design effects, stratification and cluster sampling? Any other questions about those topics before we close today? Any Zoom questions? Everybody good on Zoom? Okay, I think we're all set then. So we'll see everybody, remember 10 o'clock on Friday. Okay, so not 9 o'clock, 10 o'clock on Friday. And we'll start off with our discussion of weighting then. Okay. Okay, thanks everybody.
Thank you.
Ah, tudo bem?
Oh, yeah.